Good morning and welcome to our guests, fellow board members, Advancement Council members, faculty, staff, and friends to this year's McDowell Symposium. My name is Bob Baldoni and I'm chairman of the Burke Neurological Institute Board of Directors. I'm sorry I can't be with you today, but I'm traveling and can't be on campus. I've been connected with Burke for over 14 years, and what keeps me involved is the amazing and selfless work done here by our faculty and staff. In many of the areas of our research, we are at the threshold of some groundbreaking discoveries. And in collaboration with other great researchers and institutions, some of which you'll meet today, we hope to soon bring these cures to the bedside. I hope you'll enjoy today's program. And once again, thank you for participating in the annual McDowell Symposium. Now I'd like to introduce Dr. Raj Ratan, the CEO of BNI, who is not only an accomplished researcher, but has been a friend and the critical thinker behind the growth and development of the Institute. Please join me in welcoming Dr. Ratan. Raj, the floor is yours.
Great. Good morning, everybody. It's wonderful to see all of you on this beautiful, obviously not sunny, but very cool and comfortable morning. Can I have my first slide? Okay, great. So I was saying last night to everybody that, there's this incredible sense of euphoria that I have over being together with people in 3D instead of on a Zoom. And I think it reminds us of the fact that maybe an unfortunate fact of the human condition is that we don't really appreciate things until we lose them. And I think that it's obviously the pandemic has given all of us a chance to reflect, but being able to be here with you and break bread with you later, to hear about great talks in person, to really sort of feel the commitment of this institution, I think it's a tremendous treat. And we're obviously grateful for all of you who've made it here. This tent is really a wonderful venue and safe venue, I would say, with these with things open. So let me start by talking a little bit about Fletcher McDowell, who is kind of the inspiration for this symposium, because I think Fletcher really understood fundamentally this idea that people only value their health. But when they lose it, they really value their health. And the opportunity for physicians to be able to restore that health is an incredible privilege and a responsibility. And this is a picture of Fletcher, I think you can see, of when he was younger. And it really conveys the idea that ultimately the test of our ability to do that is our ability to impact patients. He was a very low-key, very compassionate, but incredibly driven to see changes in disability in people who had strokes or Alzheimer's disease or Parkinson's disease. And I think he's been an incredible inspiration for all of us. It was not only this idea that maybe we can restore function to people who've lost it, but also the idea that the way we get there is by doing great science. And that is also, I think, an abiding principle of the Institute. I have the next slide, please? So I don't know if Lynn Fiedelson is here, but part of, Lynn is Fletcher's daughter. His daughters have been very involved in helping us to endow the symposium, to have it as an annual event that really can celebrate his incredible vision. I want you to click, because I have a number of, click on the first one, next. Okay, so we were founded in 1978. This is for those of you who are familiar with Indian culture, this is our bio data. I wanted to go through this for you. We were founded in 78. Next, please. Our mission, as many of you know, is to cure disability from brain diseases, particularly in the chronic phase of illness. Next, please. We've been an important affiliate of Weill Cornell since 1933, and we're happy to tell you about, oh, I can do that. Thanks. Wow, a sense of control. Those of you who know me, that's... We have programs in motor, sensory, vision, and cognitive recovery that span more than 75 diseases. And we have more than 100 full-time staff and researchers. And you'll get a chance, if you wish, to have a tour of things that are going on in the Institute right behind us on this beautiful campus. But the spirit of this landscape, the amazing facilities, the sort of appropriate austerity of the buildings that were designed by McKim, Mead, and White do not tell the whole story of the Institute. The Institute is in a remarkably dynamic, collaborative, and just focused environment where people come together really with the purpose of ultimately understanding how to develop therapies that can repair the spinal cord and the brain. And this is just a picture of us at our retreat. There are a number of opportunities for us to come together, and it really is a special environment. So I wanted to tell you about some of the amazing things that are happening in the Institute. I think you'll get to meet some of the people. Obviously on the top of our list, Gary Gibson, who's sitting over there, has been working on the role of thiamine in Alzheimer's disease for more than 40 years. And last year he had a very exciting phase 2A trial, which showed really promising results with the drug benfotiamine. And that recently has been leveraged into a multi-center, almost $50 million trial supported by the NIH. And I think it is, I show this punching above our weight because it shows really how a small institute working collaboratively with Weill Cornell can be driving therapeutic development from institutions that are much larger around the country. Christina Fallo and Tomoko Kitago have been leading our chronic stroke efforts. I don't know if Joan Spivak is here, but I think she's going to come. Recently, we've partnered with government and industry to develop the first clinical trial for chronic stroke, a trial platform that really will bring together this idea that the brain is optimally repaired by modulating plasticity and as well as shaping that plasticity with experience. And this is a real, I think it's the first of its kind in the world. It's a wonderful example of how we really need government to help us de-risk trials that are highly risky, but that great science is not getting to patients, and we have to facilitate those efforts. Diana Willis has been doing wonderful work on chronic pain. As you know, the opiate crisis is upon us, and we need mechanisms to be able to treat pain, chronic pain in particular, with agents that are non-addictive. And Diana's been working with Peter Goldstein at Weill Cornell. They have a wonderful therapeutic target and agents to manipulate that target that are moving towards humans. Yutaka Yoshida has trained with Tom Jessel, has brought wonderful efforts in circuit repair. I think historically there's been a focus on molecules and cells and then on behavior in humans, but there's an important interface, and that is the brain is organized by circuits. And I think that his work on ALS and Friedreich's ataxia, I think this has been funded in part through the Hamiltons, who are one of our honorees, really is taking the field in a new and important direction. Vibhu Sani has been developing a wonderful model of pediatric spinal cord injury, and this was recently funded through the state, and it really offers an opportunity to understand why the nervous system regenerates during development, but not in adulthood. And I think it will teach us a lot about how to repair the injured spinal cord. Finally, I would be remiss by, actually I have two more. Kathleen Friel who many of you should meet because she is a leading researcher in cerebral palsy, but she also has CP. So she is, in many ways, our poster child for how a disability does not have to limit your trajectory in life. And she's done an amazing job of really identifying strategies that treat CP both in children and adults. And I want to finish with Edmund Hollis. Edmund has brought, again, circuit analysis to understanding brain repair. He just received $300,000 from the state of New York to advance a clinical trial with the Mass General focused on really improving upper extremity function in patients with chronic spinal cord injury. And it is important to mention that for the past 7 years, despite there being 17 medical schools in New York, that the BNI and Cornell have received more money from the Spinal Cord Injury Research Program, which gives more than $8 million a year, than any other institution in the state. And that means $1.5 million a year over the past 7 years. And it's really, again, a testament to the fact that even small institutions, which partner effectively with larger organizations in government, industry, and academia, can achieve remarkable things. And so I think this is only sort of a taste of the great things that are happening here, and we really invite you to take a tour because people are often really surprised by what's going on here in this small campus here in Westchester. So I wanted to finish with two things. I think many of you saw in the program that the event is about not only vulnerability but resilience. And you know, I was at a meeting in Boston last week for the foundation called Target ALS, and there was an important panel discussion about why there have been so many failures in neurological diseases. And I think one of the reasons that there are many reasons for these failures. First among them, that the brain is takes 20 years to develop. It's very, very challenging to fix problems in the brain. But the other thing is that we've had very much of a vulnerability focus, that we've been focused on disease, those who are vulnerable, those who get the disease, how their symptoms are manifest. And that while this is incredibly important, it's also important to be thinking about brain resilience. And I think one of the things that we'd really like to promote as an institute in really thinking about how to effectively repair the brain is let's look at the people who are successful from recovering. And I think Tedy Bruschi is an incredible example of this, one of our honorees. Let's study the people who, even though they are vulnerable, they ultimately don't manifest the disease at a genetic level and an environmental level. And this it really requires an understanding of those people who effectively, spontaneously recover. Why are they better? And we would really like to promote and catalyze a focus on that. And this is not a new idea. There's many examples of genetic mutations that protect from stroke and Alzheimer's disease. Many of you have heard about this town in Italy called Limone, where they found an apolipoprotein mutation that protects people from heart disease and stroke. And now recently we've found that there are mutations that protect people from Alzheimer's disease. Let's study these mutations and understand why they create resilience. But the resilience is not only genetic, but also epigenetic and environmental. Why is exercise such a consistent epidemiological factor in protecting us against disease and improving function? We have to understand these things to try to really develop therapies that will move us forward. So I want to finish, again, by thanking you all for being here. I neglected to thank members of the Institute, members of our board who are here, who contribute on uniquely to our mission, members of our advisory council who've been helping us to fundraise, obviously our speakers who have come from a long way, and our honorees most importantly, because they really provide sort of the living examples of an inspiration for all that we do here. But Glen is a much better MC than I am, and so we have asked Glen to sort of be the masters of ceremonies today. Many of you who, I hope you get to know him. He is a world-class vision neuroscientist who heads our Center for Vision Recovery, has developed really exciting new methods for monitoring vision in those who can't communicate in a very rapid way using exciting new technologies that are being licensed by companies. He's also an exemplary communicator. He's so helpful to us in our NIH grant review meetings. Yesterday, we had a Burke forum. We have this exercise every month with one of the postdocs where we have them give a talk, and then we do in-camera feedback from all the faculty. And Glen's comments are always incisive, thoughtful, and eloquent. And I think most importantly, and today is about having fun, although I apologize you won't get to hear Glen sing or play the guitar, but it's been an important part of our retreats, and that's an equally important part of the wonderful ambiance, investigative ambiance and collaborative ambiance that we've created at this unique institution. So with that, I'll turn it over to Glen, and thank you all for coming. I think we are deeply appreciative of your support for our efforts. We think that this is a looming epidemic of neurological disability, and we really need everybody's hands on deck to solve these problems. So enjoy the day, and we'll look forward to interacting with you personally.
Well, thank you very much, Raj. It's so great to see everybody here today. I'm going to be a little more stilted in my usual deliveries because of the day, and we want to keep things on time. But I want to make a few comments and then get right into our first speaker here. The reason why we're here is to celebrate. I mean, I think I want everybody to have that in mind, please. It's to celebrate the resilience and tenacity of those who suffer disability from neurological damage and disease. Of course, we have many of those in our audience today. To celebrate the legacy of Fletcher McDowell, we already heard about that, the founder of the BNI. To celebrate the work of inspired researchers whose studies are aimed at preventing and repairing neurological damage. Many people in the Institute, that's their primary focus. To celebrate and honor remarkable people who have made significant contributions to the mission of the BNI. We're going to see that very soon here. I'm so proud to actually be able to do that. It's also to celebrate the basic and clinical research that's done here at our campus. And it's actually to celebrate the campus itself. Oh yeah, as Raj said, it's also to celebrate that we can actually celebrate. I'm so excited that we're here in person, as Raj mentioned, to do this. I won't say anything more about the scourge of the COVID pandemic, but I personally, and on behalf of the Institute, I'm very grateful for our ability to be here today, and thank you very much for coming. We're all doing this by opening our doors to you and our beautiful campus. I mean, this campus every day to come to is a wonderful, wonderful thing. For those of you who are here for the first time, I have to say that New Yorkers often refer to this campus as being upstate. It's true. I think that's because they can't actually believe that there's an open space that's so beautiful that's not Central Park. So what else do you call it but upstate, right? We're sort of used to it. We come here every day, and it's easy to sort of forget that. But we count ourselves lucky to work here because of that. And oh yeah, the free parking too. It also helps. The history of the Burkenites on the 60 acres we're sitting on is fascinating, and for those who are interested in history and architecture, I encourage you to explore. I am sure you will not be disappointed. Behind me over here is the 100-year-old building that is the Burke Neurological Institute, and indeed, it has bathrooms. So you can see there's a big sign right there. Please feel free at any time to saunter up here and use the washrooms. You'll also be able to see some of the wonderful architecture and also the plant life around here. It's absolutely fascinating, frankly. Also, if you read anything, please ask any of the volunteers that are around here for any help in anything. And let me tell you about the volunteers. This is our big day, and it's all hands on deck today. And you've met many of them, I'm sure, already at the registration or parking or giving directions. They're here today to help you, and they're a wonderful resource. Please ask anyone here from the Burke, and they will give you passion, they will give you direction. They represent the mission of this institution. And you'll be amazed at not only what they work on, but how dedicated they are to the cause that brings us all here today. So with all that, let's get started. The theme of the 2022 McDowell Symposium is Hope for Stroke. Indeed, stroke is one of the greatest sources of disability in our society, and as such, it is a central focus, of course, of the research here at the BNI. Because early intervention currently provides the best opportunity to treat stroke, it is critical that stroke patients recognize stroke as an emergency and seek medical care immediately. Likewise, it is vital that the medical systems to deliver the treatments rapidly and effectively before the window of opportunity for treatment passes. Our first speaker, Dr. Matthew Fink, has made the management of stroke care a focus of his work and has made outstanding contributions to the area. You can see by his bio in the program that he has an impressive record of medical achievement. He is currently the Lewis and Gertrude Feil Professor and Chairman of Neurology at Weill Cornell Medicine and Neurologist-in-Chief at New York Presbyterian Hospital. Dr. Fink is a longtime friend of the BNI. Personally, I've had the pleasure of accompanying Dr. Fink on a trip to Weill Cornell's affiliate campus in Qatar, and I have had the opportunity to experience his dedication and passion up close. Please join me in welcoming our Cornell colleague to the BNI for his presentation entitled Pre-Hospital Stroke Care and Mobile Stroke Treatment Units. Excuse me, Dr. Fink.
Thank you. Can you, all of you hear me? Great, okay. I'm like a hyperactive child. I have a very difficult time standing behind a podium. I like to move around. I'm delighted to be here. I want to thank Dr. Ratan for his gracious invitation, asking me to participate. Most important, I got to put on a real suit for the first time in about 2 years, and it feels pretty good. It feels pretty good. So my mission in life, and I mentioned this last night, it has always been to do everything possible to improve the care of patients with neurological disorders, and stroke is one of the biggest ones. And we have made incredible strides in identifying patients at risk, preventing stroke, and treating it acutely. And I want to share with you some of the new developments that have come along that really are going to change this field even further. So what's a mobile stroke unit? And we'll get to that in a bit, but let's review the importance of the problem. The World Health Organization has identified the 10 most important global health issues, and it turns out that 4 of them are brain-related. Stroke is number 1, second leading cause of death in the world. Dementia, traumatic brain injury, depression. So we have a lot of work to do in this field, but stroke is certainly one of the biggest. And in the United States, we have almost 1 million people are affected by stroke. And even though we have made great strides in reducing the incidence of stroke because of the aging population, and since age is the #1 risk factor, the numbers are still very high, and they will continue to be high. Now, in the US, we've done very well. It's the 5th leading cause of death, and I'm not going to say much about COVID. I'll just mention it. One thing, in the past year, in the United States, COVID has been the third leading cause of death of everything, okay? So we'll have to keep that in mind. But in terms of the effect of stroke, it's the leading cause of disability for adults. It's the number one reason that a person ends up in a nursing home, and none of us want to be in that position. We want to avoid that in every way possible. This is a CT scan that I have been using since the 1980s. And in the 1980s, when I took this CT scan from a patient of mine, there was no treatment for stroke, literally nothing. This is a devastating stroke that killed off about half of this person's brain. She remained alive. It's someone who had atrial fibrillation. A blood clot went from the heart to the brain and caused a massive area of damage of the brain in the middle cerebral artery on the right side of her brain. She survived, but was devastated, wheelchair-bound, bed-bound, never able to resume any type of quality of life. We can prevent that now, and we can treat patients like this now and avoid something like this from ever happening again. So how do we do that? Well, you've all heard about clot-busting drugs, what we refer to as thrombolytic drugs, which can break up a blood clot that goes to the brain. These were demonstrated to be effective in the mid-1990s, and since that time, it has been the standard of care. But what we know about this is that every delay in administering this drug results in worse outcome for the patient. And we can plot this literally every 15 minutes. Every 15-minute delay in IV thrombolysis worsens hospital mortality, reduces the recovery, increases the risks of hemorrhage, and decreases the likelihood that the person is going to be able to go back home and live a normal life again. The drugs are easy to use, easy to administer, and they work extremely well. So what's the problem? Why are we having difficulties in treating as many patients who could potentially benefit? Well, these are numbers from about 10 years ago, where we targeted treating patients with a thrombolytic agent as soon as they got to the hospital, and we gave ourselves a 60-minute time window to do it as quickly as possible so there'd be no delay. And at that time, at our hospital, everyone was treated within 60 minutes, and most academic medical centers were doing the same thing. But it turns out that's not enough. And the reason it's not enough is that it takes too long for patients to recognize they're having a stroke and to get to a hospital where they can be treated. So how can we speed up the process? Well, the first thing turns out to be teleneurology. Telemedicine is just a spectacular advance, and we really learned this through the pandemic, where we were doing telemedicine for virtually everything. So here we have a neurologist sitting in her office, but it could be sitting at home, it could be sitting in my car, anywhere really. You can do this with a cell phone, an iPad, a computer, and the neurologist is communicating on video with a patient who has symptoms of a stroke, and that can be diagnosed within 5 or 10 minutes via telemedicine without having to have anyone travel anywhere. And there are studies that have shown that it is just as reliable and accurate as doing this in person. So teleneurology is a tremendous advance. So it's also good because there's a shortage of neurologists. We don't have enough stroke neurologists to be able to do this. So with teleneurology, we can leverage these scarce specialists, speed up access for the patients, rapid triage, rapid accurate diagnosis, and also, if you worry about such things, it saves a lot of money. Just imagine the difference between a phone call on video compared to everything that goes along with an in-person visit. So it saves a lot of money as well. And what grew out of this model is what we refer to as a hub and stroke model for stroke care. So On the one hand, we have the physician who can be anywhere, really. The physician can be at home, can be on vacation, doesn't matter. Could be sitting here, and you could do it on your phone if something happened. And then we have a local community hospital that can provide the initial stroke care, but helps to then triage which patients need more advanced care and are then referred to a comprehensive stroke center. Now, why would we do that? The thrombolytic drugs can be given anywhere, but there are some patients who are going to benefit from a more complex intervention to remove the clot, literally, from the artery in the brain, if that's what it takes to treat that patient. So we have to triage which patients are going to be best treated that way. This is a study that was published 10 years ago from UPMC, where they have a huge hub and stroke network. This is one which is a 7-hospital system, but UPMC now has a hub and stroke network which includes 36 hospitals. 36 hospitals are part of their network. And the bottom line is that this system not only improves care for the patients, but saves an incredible amount of money. In this case, if you look at the negative $358,000 a year saved, that's per year, money saved by using a hub and stroke system where you don't have to unnecessarily move all of the patients to a comprehensive stroke center. So having a neurologist by telemedicine and a hub and stroke system has a tremendous impact in care. And this is data that Jeffrey Saver from UCLA put together years ago, and I just love to quote this. The time to treat impact on stroke outcomes is truly unbelievable. Look at per minute. For every 1 minute of delay in reestablishing blood flow to the brain, when someone has a stroke, you're going to lose 1.9 million brain cells per minute. Per minute. This is a tremendous impact. So every minute truly counts. And if you were in our emergency department when a stroke patient comes in, it's the only condition where our staff are literally running with the patient on a stretcher from CT scan to the emergency department, literally running to save every possible minute that you can save, because it makes a big difference. And so we know that with these thrombolytic drugs, we have to administer them within 4.5 hours of onset of symptoms, or they're not going to help. That's what this curve shows. After 4.5 hours, there's really no benefit in administering these drugs, so time is really critical. So how can we speed up the process? I'm going to just skip over this one. How can we speed up the process to deliver these treatments faster? Well, let's talk about ambulance-based telemedicine, okay? It's easy for a neurologist to communicate with an ambulance by telemedicine and communicate with a patient, but you can't really diagnose a patient with an acute stroke and decide on treatment with telemedicine alone. So in 2003, Klaus Fassbender, who's a stroke neurologist in Germany, sent a letter to the journal Stroke and proposed the development of a mobile stroke treatment unit. This is a picture of it. For hyperacute stroke treatment, the unit will go out to the site of where the patient is. And the key to really doing this is there's a CT scanner that is installed in the unit so that diagnostic studies can be performed. All of the drugs that are needed are on the stroke unit. So the stroke unit goes to the patient, makes the diagnosis, treatment is administered, and by doing that, a lot of time is saved. Now, he went so far as to actually say, if you read the small print, which I'm sure you can't, he actually specifies that the ambulance should be a Mercedes-Benz ambulance, which I found was kind of interesting. He went into great detail. So he was the first person in the world to propose it. and started doing it in Germany. And why is this such an amazing thing? Well, you bring the physician and the diagnostic tools to the patient, initiate treatment on the scene, cut time to treatment, and we increase the chance that we're going to successfully give thrombolytic therapies to a patient having an acute stroke. This is what it looks like. This is actually our first unit. This was a practice run when we were just training everybody how to do this. We started out with an onboard neurologist, 2 paramedics, a CT scan technician who turns out to be extremely important because when the CT scan gets bounced around the streets of New York City, it needs to be constantly maintained and repaired. And then we carry all of the appropriate medications with us on the unit so they can be administered to the patient. Now, this is the data that Fassbender first published in 2013, showing that compared to every other published study on rapid treatment, the fastest was on the mobile stroke unit. He's at the top. All of these others are studies that looked at how quickly thrombolytics could be given in a hospital. But you can give them a lot faster if you go out in the field and do it right where the patient is and don't wait for the patient to get to the hospital. So he proposed this in 2013. I was aware of this. I got very interested. It took me 3 years to convince our hospital leadership to do this. Those of you who know me, I'm a very persistent person. I just wouldn't take no for an answer. I kept going back over and over and over and over again. So in 2016, we finally launched our first unit in New York City. And the algorithm is the same thing as what we would do in a hospital emergency room. The patient is examined, a CT scan is obtained, a diagnosis of acute stroke can be made, and then thrombolytic drugs are given right on the ambulance. And this is done extremely rapidly. Then the patient is transported to the hospital if further evaluation and treatment is needed. But in reality, many of these patients, if they're treated so early, are virtually recovered by the time we get them to the hospital. This is the only situation where I've seen such rapid recovery, and the reason is if you give the thrombolytic drugs very early, the clot dissolves much more quickly. The longer you wait, the harder it is to dissolve the clot. So this is data that came from the Berlin group that really was doing this earlier than we were. And if you look at the what we call a modified Rankin score, that's a measure of disability, they demonstrated that their patients as a group recovered better than compared to conventional ambulance transport. But the thing that to me was most exciting is if you look at the bottom of this slide where it says time from onset to thrombolysis less than 60 minutes from onset of symptoms, 37% of the patients were treated from onset less than 60 minutes. This is what we refer to the golden hour when a blood clot is soft and can be dissolved very, very quickly. That never, ever happens in a hospital emergency room because the people just don't get there fast enough. An illustrative case, I'm going to go through this just very quickly. A 41-year-old man, he was an attorney, perfectly healthy, had a major stroke on the way to work. Hemiparesis, left-sided paralysis, global aphasia, couldn't speak at all. The unit was dispatched. He was treated on the ambulance with thrombolysis. He was almost fully recovered by the time he got back to the hospital. And it turned out, well, why did a 41-year-old man have a stroke like this? Well, it turns out he had atrial fibrillation that he didn't know about. And that's what happened. But in the meantime, we saved his life and saved his ability to get back to a normal life. And we've seen this happen over and over and over again. From the 4-year period up until the pandemic, from 2016 to 2020, we operated 3 units, 1 in Manhattan, 1 in Brooklyn, 1 in Queens, and we treated with thrombolytic drugs, as you can see, over about 250 patients with thrombolysis. An amazing outcome as well. Treatment times are much quicker when we use the mobile stroke unit than if we wait for patients to come to a hospital. And then we participated in a national trial of multiple centers because really we have to prove to the general public, prove to the federal government that this works in order to get reimbursement. This entire program was operated from philanthropic funds, entirely. So we cooperated with several other cities led by Dr. Jim Grotta in Houston, and we published the data last year. We got a lot of publicity when this was published in the New England Journal, and what we showed is that the time to treat was at least a half an hour quicker, which ultimately resulted in an improvement in patient outcomes. So if you look at these two rows, patients treated with the mobile stroke unit had a higher percentage of patients who have what we call a score of 0, which is normal. They're completely back to normal, no impairments, no deficits, no problems whatsoever. 100% recovery, much higher probability of that happening if they're treated on the mobile stroke unit. Not advancing. Well, in any case, I got it. So this is an international program. As you can see, there are countries all over the world that are doing this now. The largest numbers are in North America and in Western Europe, but it's growing and expanding all over the world. And again, this is part of a growing system of care to identify patients who are at risk for stroke, treat them as early as possible, return them to completely normal health and normal lives. And that's really our goal for all of us who are here. So I thank you for your interest, and I'd love to hear your comments or answer any questions.
I think we have time for a question or two.
Thank you, Dr. Fink. That's amazing. My question is for those of us who don't live in major metropolitan areas, what size or population density would be required to be able to afford or pay out a unit?
Yeah, well, it's a great question. What we discovered is that no matter where you live, there's a benefit. And now, when we first started in New York City, people said to me, "You're crazy in New York City. There's so much traffic, the ambulance can't move anywhere." That's true, but it's still the difference between a one-way trip as opposed to a two-way trip. You still save a lot of time, and in lessly populated areas, the ambulance gets to your house faster than it would be if you had to go to the local hospital. And that's been proven. One of the programs is in Alberta, Canada, and they service a largely rural area outside of Alberta, Canada, and they found the same thing. So any way you look at it, it's going to be beneficial. I've had a couple of patients who said to me they wanted to buy a unit and have it parked next to their house. Now, that is not a good use of a unit. That we would not agree with. Even though they were going to write a check, I said, nope, we're not doing that. That's not a good use of it. It needs to be moving around. It needs to respond to the community.
Okay, one more question, thanks.
I was just curious, since the publishing of your article of the study, have you gotten sponsorship from private insurance or government sponsorship for these units?
No.
Why is that?
Well, why is that? Simple. They don't want to have to pay for it. Here's the problem. For those of you who understand how our health insurance system works here. In Europe, most of the countries have a single payer system. So they don't mind an expense up front, which is going to save a lot of money downstream. In this country, the insurance companies are like, well, this is great. You pay for this ambulance, and we will save the money because we won't have to provide health care to these patients because they're going to recover from their stroke. So they don't want to pay for the extra costs. They're already saving the money. The same thing applies to the Medicare program. The Medicare program saves money. We incur the expense. So we have to get a real lobbying effort to get the federal government to really pick up the cost of this through the Medicare program. But so far, they have not agreed to do it.
All right, thank you.
Thank you.
Matt.
I should be at the store.
I didn't say that, you did. Thank you very much. What an exciting way to start the symposium. That's just fantastic and right down the road. So thank you very much for kicking us off. I can't believe these papers that I'm looking are like limp. Look at them. It's the most humid day today. So wonderful. We kicked that off, and we have actually a design to the order of the talks and so forth today. And so we wanted to start with a clinical talk, and we're going to work our way deeper into the details of how brains structure and work, of course. But whereas early interventions currently represent the best opportunity to treat stroke, protecting the brain from stroke damage is an inviting opportunity for intervention. The approach, however, has had a mixed record. There have been lots of promise at the basic research level in protecting the brain after stroke, but few interventions have proven effective in clinical studies. Our next speaker, Dr. Dennis Choi, is particularly well-known and decorated neuroscientist who has made seminal contributions to basic research in neuroprotection and sees opportunity to build on previous studies to develop effective interventions to limit or prevent stroke damage when it occurs. Dr. Choi is currently a professor of neurology at Stony Brook University, but as you can see from his bio in the program, he has been a leader at numerous academic and biotechnology institutions and has been recognized with many of the highest medical and scientific awards for his research. This guy is a real superstar, I have to tell you. We are honored to have Dr. Choi with us today at the McDowell Symposium. I met him for the first time in person last night. He is absolutely a delight to talk with. Would you please join me in welcoming him for his presentation with the provocative title, Stroke Neuroprotection, Getting Back in the Water. Dr. Choi, I hope this will work for you. Thank you.
Thanks, Glenn. Thank you, Glenn. I'm honored to be here and contribute to the celebration of Dr. McDowell, the Burke Institute, and the McDowell awardees. Raj, thank you so much for inviting me. So, let's see slides. As you can see, my title changed. At the 11th hour, I decided this audience might find it more interesting if I drilled more specifically into one class of potential neuroprotective agents, NMDA antagonists, rather than talk more generally about prospects for developing neuroprotectants as a whole. So that's the title of the talk. As you can see from this title, NMDA antagonists have been tried, and that's the checkered past and failures. That was version 1.0, and what I'm going to try to make a case for today is the idea that that shouldn't completely turn us away from this approach, and that maybe version 2.0 is worth attempting. It's got a lot of buttons. The green one. There we go. Okay. First, I do have to disclose that I am an active scientific advisor to several biotechnology companies, two of which, Algernon in Canada and Gnt Pharma in South Korea, are specifically working now on developing neuroprotective drugs, breakthrough drugs. And I will be showing a little bit of GNT's data today. So stroke is very familiar to the Burke community, as Dr. Fink expertly reviewed. It is a leading cause of death and disability requiring rehabilitation worldwide. The goal of developing effective acute therapies for stroke has fantastically appeared in recent years, as Dr. Fink reviewed, with the advent of clot-busting drugs and surgeries, endovascular surgeries. But these clot-busting drugs that remove a blood clot that forms in an artery and blocks off blood flow to a brain, causing ischemia, only work, are only applicable in a minority subset of patients with the right kind of clot, right kind of vascular anatomy. The larger population of people who experience strokes are not suitable for these approaches, unfortunately. So the bigger part of the black box, the gold box of developing acute therapies, is the hope of developing drugs that render the brain less vulnerable to a given ischemic insult. Is this possible? Absolutely. If you were to take a blood pressure cuff and tie it around your arm and blow it up for 5 or 10 minutes, it would be uncomfortable. Your arm would be cold and blue, numb. But if you took the cuff back down and shook it around, after a while, your arm would be fine. You would not want to try that around your neck. So the brain is much more vulnerable to an ischemic insult than most other body tissues, and understanding the biological basis with this greater vulnerability should provide approaches to reducing vulnerability and protecting the brain. One major avenue to developing neuroprotective approaches, or said as a mirror, one major reason the brain is so much more vulnerable to a given ischemic insult than the arm is excitotoxicity. What is excitotoxicity? The brain's biggest transmitter, most prevalent neurotransmitter used by a vast majority of central neurons in the brain and also spinal cord, is glutamate, an amino acid. This was identified a long time ago, 50s and 70s, and then surprisingly, it was discovered in the 50s and 60s that glutamate could actually kill central neurons. It's used as a signaling molecule. It's released in little brief pulses. It's how we work. It's how we think. But if something goes wrong and it's released in a more sustained fashion, that sustained exposure can be cytotoxic, kill brain cells. Initially, this caused a lot of concern about exogenous glutamate, monosodium glutamate. It turns out that you can probably eat it fine. Lots of Chinese would say so. And you don't really absorb it, and it doesn't get into your brain, it doesn't cause excitotoxicity. But in the 70s, people began to think about the possibility that the large amounts that we carry around and use all the time for our thought processes might, under disease conditions, come out abnormally and kill cells. And this became initially of interest in the setting of chronic neurodegenerative diseases, Huntington's disease, Corlin-Schwartz, McGeer, and also epilepsy, specifically epileptic brain damage. The brain damage is caused by sustained seizures where a lot of glutamate comes out. It seemed like a setting where excitotoxicity might take place, and this idea stands today. The idea that glutamate might contribute to ischemic brain damage, stroke, was surfaced in the 80s, and two pivotal studies, one by Steve Rothman and the other by Roger Simon and Brian Meldrum in 1984, demonstrated that glutamate antagonist drugs, what happens when glutamate comes out is it binds to receptors on brain neurons, and if it's there too long, it overstimulates these receptors, the cells sustain injury and die. And if you block that interaction with a molecule, an antagonist drug, those investigators showed that it reduced anoxic ischemic injury either in cell cultures or in animals, and thereby demonstrated that this principle of excitotoxic ischemic brain damage might be the real thing. My entry into the field occurred in the mid-'80s. Excited by these observations, I began to ask, how does glutamate kill cells? What's the process? The early idea was that it was just overexcitation, which sort of in a broad sense made intuitive sense, hence the term excitotoxicity. But it turned out that if you looked in more detail, the excitation that glutamate produces is largely mediated by sodium ions entering brain cells through channels opened by these glutamate receptors. But was more prominently responsible for excitotoxic cell death was excess calcium entry. And it turned out, and this is work from Amy McDermott and colleagues at Columbia, that all glutamate receptors are not equal in terms of driving calcium in. They all drive sodium in. They all excite. But the NMDA class of glutamate receptors is disproportionately important in moving calcium into brain cells. So that gave support for the idea that the NMDA receptor might be especially important in mediating excitotoxic ischemic brain damage. So a whole bunch of companies began to develop NMDA antagonist drugs that would block the NMDA receptor and reduce calcium entry during an ischemic insult. And lots of laboratories showed that if you gave these prototype drugs to rats in an experimental stroke, you could protect the rat brain from an ischemic insult. So this was an old experiment that I believe was done by Chung Shu back at Washington University. And you can see in the control, it's like a slice, the brain is cut like a loaf of bread. You can see the white area is an infarct. That's dead brain, big chunk of dead brain that occurred in the rat's middle cerebral artery territory after Chung and his colleagues tied off that artery to mimic what would happen in a human stroke. You can see below a similar situation in a rat that was given an NMDA antagonist drug to block that calcium entry, and you can see the stroke was reduced. And this was a very robust finding. Many laboratories throughout the world showed this basic result. You had to give the NMDA antagonist very quickly, though, ideally pre-treatment or within minutes to, at most, a couple hours after tying off the artery. So this is all very exciting. A lot of companies developed NMDA antagonists, including a company that I would later work for, Merck, but they didn't work, and that's the failure part of it. So this was a particularly good study. It was carried out by Ciba-Geigy, now Novartis, and they developed this drug 19755, and you can see the bottom line, the modified Rankin type scale at 3 months, and you can see that patients treated with Selfatel, their candidate NMDA antagonist drug, did not do better than patients who received placebo. In fact, if you looked at mortality and brain-related mortality, there was a very scary suggestion that they did worse. So the idea didn't work. So thought leaders in the field appropriately wrote epitaphs. This one I like a lot. It was, among the authors was Alistair Buchan, a friend, who went on to become dean of the medical school at Oxford. Notice, though, that Alistair and his colleagues were always very thoughtful. They didn't rule out the possibility that an NMDA antagonist might someday be useful. They actually said it remains to be proven, because there were reasons to be a little doubtful about the overall pervasiveness of the evidence against NMDA antagonists. Why did these NMDA antagonists fail? Version 1.0 NMDA antagonists fail. Well, the first and most important reason was simply that they were all given too late. Basically, at that time, unlike the modern era that Matt Fink described, it really wasn't possible to get to patients and treat them quickly enough. Remember, I mentioned that in a rat, if you really want to treat rat stroke, you've got to get in there within a couple of hours, ideally even minutes or pre-treatment. Humans were treated way later. Nobody was treated less than 3 hours, and some of the studies went out a day or two before giving the drug. It was just what you could do. There weren't stroke units. There certainly were no mobile stroke vans, so that's what they could do. So really, you can't look at that evidence and say NMDA antagonists don't work. We know that because the drugs were all given too late. And then secondly, a number of us are of the mind that these version 1.0 antagonists weren't quite right. They were all NMDA class antagonists, so they all interfered with calcium entry, but they were so-called broad NMDA antagonists, subtype unselective antagonists. And we now know much more about NMDA receptors, and as you would guess, there are all these different flavors of NMDA receptors, subtypes. These are subtype unselective, And the paradigm was full hard block. Let's just block those bad NMDA receptors out. And there were a lot of side effects associated with doing that, maybe sort of intuitively something you would guess. And secondly, a specific idea that I'm still currently fond of that emerged during this time in the later 90s when I was at Washington University was a thought that whatever benefit was achievable with this late delivery of NMDA antagonists might have been masked by a downside, and that specifically reducing calcium entry excessively, remember hard block, all the NMDA receptors, might have actually promoted another type of cell death called programmed cell death. So this is a very exciting and big topic driven by the Nobel Prize winning work of Robert Horvitz and others. And we know that programmed cell death is extremely important in many forms of tissue injury, certainly neurodegeneration, and it's important in ischemic injury as well. And at that time, the understanding was emerging that programmed cell death was actually facilitated by lowering calcium. So we started to think, what if in these trials people drove calcium actually too low? So you got some benefits by blocking out excitotoxicity, but you worsened ischemic apoptosis, programmed cell death. So really, I think it's fair to say that the NMDA/excitotoxicity hypothesis has not yet been tested in humans. And in fact, knowing what we know today with the uncanny clarity of the retrospectoscope, one would love to go back and do it with version 2.0 antagonists and use Dr. Fink's mobile stroke fan. So I'll flesh this out a little bit further for the aficionados here. Basically, the model is that the ischemic insult causes all this glutamate to be released from nerve terminals and also astrocytes. This flooding of glutamate, which was identified first, I think, by Niels Diemer in Copenhagen, just sits out there and causes cells to die, a fulminant, calcium-driven, excitotoxic cell death. And I believe, many people still believe, that is happening in human stroke. But there is this other pathway, which happens when the insult isn't quite as intense. And that means as the cell is injured, as investigators like Horwitz and others identified, internal cell surveillance mechanisms and signaling pathways are triggered that are designed to take the cell out quietly. It's very adaptive for a cell that's injured to say, okay, I'm not going to make it. I'm going to disappear quietly. I'm going to execute programmed cell death that will be the least disruptive for the tissue around. So these mechanisms take place. And as I mentioned, there's sort of a reverse calcium dependence. The upper arm is driven by calcium overload. The lower arm can be triggered by calcium overload. That causes an injury. But if the overload isn't massive, then there's a reverse dependence. And calcium starvation actually accelerates this lower pathway. And if you think about the difference between human stroke and rat stroke in the laboratory, the rat has a bullet-shaped, smooth, so-called lissencephalic brain, and you tie off an artery, boom, click it off, and this sharp infarct occurs. That's going to favor the upper pathway. Human stroke, we have this gyrencephalic brain, lots of hills and valleys, complex watersheds. Human stroke stutters, things are always messy. There's a lot of intermediate injury involved. That's going to be a greater amount of programmed cell death. And so that would be yet another reason why something that worked so nicely on rats didn't work in humans. In fact, it's actually possible to demonstrate programmed cell death in rat stroke. You just have to take the insult down to a threshold, just as this thinking would suggest. This was an experiment carried out by Chung Du. We coined in the lab, and we coined the term very delayed infarction. The lower row, D, E, and F, is basically the standard rat stroke model. You tie off that artery, a day later, which is D, you get this nice infarct, and it stays there and gradually gets resorbed. That was standard, and it was conventional in the field at the time to assess a stroke a day after, sometimes even 12 hours after tying off an artery. But what Cheng Du identified was that if you graded that down to just a threshold insult, you could actually create a rat stroke that looked like the top row. And that is, a day later, it actually was no infarct. So it looked like you didn't do enough. But then if you went back, which the field wasn't prone to do, and looked 3 days later, you could start to see an infarct blooming. And in fact, it got to be pretty big if you went out a week later. So this sort of gradual cell death caused by a threshold insult was in fact programmed cell death. And since Jin-Moo is here, I'll mention that some nice work that he did back in the day was to identify zinc as a driver, a loss of zinc homeostasis as an important driver of this ischemic apoptosis. This idea of this reverse calcium dependence at all is mostly on the blackboard, but Lorella Canzanero and Stefano Sensi did an experiment to provide some direct support for the idea. What they did is they took our cell culture model. We would take cultured neurons and take away the oxygen and glucose, and the cells would die in excitotoxic death, NMDA receptor driven. If you block the glutamate receptors with drugs, the cells in the culture were then resistant, more arm-like in their resistance to ischemia. And we call that blocked oxygen glucose deprivation. But you could still eventually kill the cells. You just kept increasing the duration of oxygen glucose deprivation. And in blocked OGD, then you saw apoptosis, programmed cell death. And what Lorella showed here was that, of course, regular excitotoxicity, the calcium levels go through the roof. In blocked OGD, the calcium levels actually sunk below normal. And another parallel experiment, if you just block glutamate receptors, you could cause the cells long enough, you could cause the cells to die, just from that alone by calcium starving them. And in fact, in this experiment, she showed that if you normalize the calcium by actually artificially increasing calcium entry with a drug, you could save the cells that were undergoing blocked OGD. So this is some evidence for this reverse calcium idea. To put it together on a sort of concept slide, this diagram may be useful. What it suggests, if you look along the vertical axis, that dotted line, it embodies the concept that an insult, if at a threshold level, will induce a cell, will trigger a cell to activate its internal death pathways and undergo apoptosis, programmed cell death. But you can blow through that by hitting a cell so hard, damaging a cell so badly that it's not able to activate its internal signaling mechanisms and undergo suicide, programmed cell death. It just dies. The metaphor I like to think about is you take a cell and put it on the sidewalk and you stepped on it, the signaling pathways aren't going to do much. It's pretty much blew through them. So that's necrosis, and that's what happens when calcium just goes through the roof. There's really not too much that you can do about it. The cell's just going to go. And the other concept is the calcium dependence of necrosis versus apoptosis. And as I mentioned, low calcium in a number of experimental paradigms favors programmed cell death. So here's another way of showing this NMDA antagonist version 1.0 fallacy hypothesis. And that is, what if you were in the zone of excitotoxic necrosis and calcium overload, and you started to block out all those NMDA receptors as hard as you could, and you shot through the green zone, which is where you were trying to get cells into a survival zone, and you moved them into promoting programmed cell death, and then you didn't come out ahead. So this all doesn't happen at once. Everything in stroke is messy. Different parts of the brain are undergoing different parts of this process concurrently. But in a very, very broad sense, the early stage of a stroke is likely when the flood of glutamate is occurring and excitotoxicity is triggered, intense NMDA receptor overactivation is occurring, and that's where experimentally even version 1.0 antagonists were beneficial in laboratory models. That's the triggering phase, and that's minutes to maybe an hour or so. But then you move into this modulatory phase where the intracellular calcium levels, in fact, have the potential to work both ways. And if you lower too much, you can actually promote some of these cell death pathways. And then later on, in the hours to days level, you have the steady execution of the steps that finally kill the cells, including activation of catabolic enzymes and lots of oxygen and nitrogen-free radical reactions. This, of course, taking place only slowly if it's in the more programmed cell death mode. If you step on the cell on the sidewalk, not much to do about that or say about So is it in fact possible that knowing what we know now, we could redevelop NMDA antagonists as a neuroprotective treatment for stroke? I think the answer is yes, and there are now at least two companies, two that I am aware of, that are actively pursuing this idea. And I just wanted to tell you about that to hopefully get you excited. The first company is a Canadian company based in Ontario. It's founded by Michael Tymiansky, who's head of neurosurgery at the University of Toronto. The company is NONO, or I think he sometimes says NO, which is actually the way he thought of the name. NO is nitric oxide, which is one of the free radicals, which is generated from many causes, but in particular following NMDA receptor overactivation, calcium overload. You activate nitric oxide synthase and generate this gas, free radical, which is very cytotoxic. So he said, let's interfere with this. But then I think a brilliant approach that he and his company now have taken is say, you know, this calcium stuff's kind of messy. Let's leave the calcium channels alone. And let's focus on another way that NMDA receptors activate NOS, which is actually not through calcium, but through a direct protein-protein interaction. And so this is a signalosome signaling mechanism. And what he did, further thinking about this array of NMDA receptors, it turns out that they're not all equal in mediating ischemic brain injury. Probably the so-called NR2B subtype of NMDA receptors is disproportionately important. So he went after that and he said, let's interfere with NR2B's handle on this signalosome and its activation of nitric oxide. He came up with a designer peptide. It's a 9-amino acid peptide that is based on the carboxy terminal 9 amino acids of the NR2B receptor. And it interferes with the ability of this protein to activate through protein-protein interactions nitric oxide. So it's a nice way of bypassing this whole calcium mess and saying, let's go NR2B, nitric oxide, and see if we can get a protective effect. So that's the drug. They called it NA1. And it showed promise in clinical studies. So this was a study that was published in 2012, and he basically was able to give this shortly after surgery in a group of patients who were receiving endovascular coiling for aneurysm surgery. And you can see that it worked. Basically, the result is statistically significant. And the group of patients that received NA1, this peptide version, I think of it as a version 2.0 NR2B antagonist, had fewer infarcts than the group of patients that did not receive the drug. So this was very exciting and very promising. Unfortunately, a larger study in a different population was not positive. So this was just recently published in 2020. This was so-called ESCAPE. And in this study, these were stroke patients, not endovascular coiling aneurysm patients. These were stroke patients treated with NA1 within 12 hours, who all were candidates for endovascular surgery. And you can see, and basically it didn't work. He was not able, this study looked at 1,000 patients, did not demonstrate a benefit of NA1. However, at the end of it all, they looked and they realized that the subset of patients, and this is their data, and I put a box around it, who did not receive the clot-busting drug TPA, alteplase, actually benefited. So you see that there, that the number of patients achieving a good outcome, MR modified Rankin 0 to 2, went from about 50% in placebo to 59% in the group that received alteplase. And this is statistically significant, although it's a post hoc analysis, it's illegal. But it suggested that there might be a benefit in this subpopulation. And as the authors suggest, and I find this very plausible, this is actually fully understandable. What they figured out, sadly too late, was that there was a likely drug-drug interaction between TPA, alteplase, and NA1. And what happens is that alteplase actually destroys NA1. The way it does is it generates plasmin from plasminogen, and plasmin chops up NA1. And they actually came up with evidence both in the rat animal model and in looking at subsets of clinical data that this was going on. So it's, I think, pretty plausible that this unfortunate drug-drug interaction wiped out the benefit, wiped out the drug, wiped out the benefit in all the patients who received TPA. And if you look at the subset who didn't receive TPA, the drug worked. So I'm still very excited and encouraged, and we shall see. They do have another large phase 3 study going on, and it should be concluding soon if it hasn't already. It's called Frontier, and they're going to look at a group of patients who are going to receive this drug in the ambulance. One great thing about neuroprotective drugs is you don't have to separate hemorrhage from ischemia, so you can actually safely give it in the ambulance without even a stroke van. So we shall see. Frontier coming out. Lastly, I do want to tell you about the second approach is Gnt Pharma that I mentioned. Gnt Pharma was actually founded by a former fellow of mine, Byung-Ju Gwag, who after his Washington University days went back to South Korea and started to work on the development of new chemical entities that might be useful in stroke. And their lead candidate now is a drug called NAU2000 or Nalanimdes. And what BJ did, as you would guess, is his company developed an NR2B selective drug, and they made it weak. So his approach was, to block the NMDA receptor, but only the subtype, so not all of them, and to make the block weak. So a low affinity or technically a high off-rate drug, so you wouldn't take out all the calcium. You're not going to get as much excitotoxicity, anti-excitotoxic benefit as you would with a big antagonist, but you also won't cause calcium starvation. And then he coupled it with a powerful antioxidant moiety, which for the aficionados, at least head-to-head in vitro, appears superior to Trolox, edaravone, or NXY-059, drugs that were tested in stroke. So it's a double molecule, multi-targeting approach. This drug has just completed its phase 2 testing. One study, Sonic, was just completed in Korea. It's really like the Canadian study. These are patients who were all receiving endovascular therapy. And this is unpublished, but this paper is in the review pipeline, so it should appear pretty soon, I hope. It did not achieve statistical significance overall. It was a relatively small n, but there is, I think, reason for encouragement. If you look specifically at the modified Rankin outcomes at 90 days, standard outcome, you can see in the lowest bar, that's the MRS0, the patients who, as Dr. Fink indicated, basically make a full recovery. The numbers went from about 14% in placebo to nearly 30% in the high-dose group and intermediate in the low-dose group. So that was especially encouraging. And in general, there's a positive shift, as aficionados can see, that makes a reasonable odds ratio. Not itself, doesn't itself make the case, but it's enough encouragement to keep on going to phase 3, which they're now doing. Additionally, the possibility of benefit from this version 2.0 antagonist is supported by a parallel study that was completed in China. This is more of a general stroke study without endovascular surgery, et cetera. And you can see here, if you look at the bottom, also unpublished work, there's a positive, meaning favorable shift in the outcomes in the patients who received this drug, Nalanimdes, soon after the onset of stroke, within 6 hours. And in this case, the study, I think, was particularly handicapped by a very good outcome in general. So if you look at the placebo, you get to be about 70 plus, more than 70% had a good outcome anyway. So you have a real sort of ceiling problem. But there's still a shift to better outcomes in the drug-treated group. So I'm holding my breath and hoping that this drug also makes it. Finally, we shouldn't say, let's say these drugs don't work. I mean, have to say that after all these failed trials, failure is perhaps more likely than success, but you never know. Does that mean that we should give up? Absolutely not. Certainly not on neuroprotection, and I would say not even on NMDA antagonists. Knowing what we know today, I can already start to see what version 3.0 would look like, and I do want to leave you with that. You could improve targeting in time and space. You could identify patients who have particularly prominent active excitotoxicity. You could ideally hammer that that early phase harder than perhaps GNT is doing. If you had a very short-acting drug, so you could block it out and then lose the effect before you got into calcium starvation. You might, using catheters, be able to restrict and target the action of these drugs in space to areas of the brain that are undergoing acute excitotoxicity. And lastly, you certainly could do a lot of more multi-targeting. Multi-targeting is something that the neuroscience community has not done enough of, in my humble opinion. Our colleagues in fields like infectious diseases or cancer routinely use multi-targeting. They have many drugs that don't work by themselves, but combined with others work. That's standard. Neuroscience has persisted in trying to develop drugs on their own, one by one. You know, what if you needed to have nerenatide and nilomadase on board? On paper, they look synergistic before you could get an effect. Or, for the aficionados, in the 20 years that have elapsed since version 1.0 failed, we know a lot more about excitotoxicity. We know a lot more targets that amplify the ionic derangements associated with excitotoxicity. Just very fast for the aficionados, they include the TRP receptors, especially M7, the acid receptors, the SEECs, the pannexins responsible for ischemic depolarization, ampakine receptors, volume regulatory receptors on astrocytes, VRACs that are involved in glutamate release. You have a lot more ionic derangements besides calcium or even just sodium. You have zinc, hydrogen, potassium, and you have all the effectors, the free radicals. And finally, we know a lot more, and Raj has been a pioneer in this field, about intrinsic cell death mechanisms. So it's not just vanilla apoptosis, but a number of other ways in which cell signaling pathways can cause cells to commit suicide, and that includes the ferroptosis that Dr. Ratan has worked on, parthenatosis, and others. So why stop at one? What if we needed to hit more than one of these things to break through to neuroprotection? Thank you.
We have chance for one quick question, please. Got somebody, Diana?
Anybody? Oh, over there.
There's
Emily's got you.
Sung Hee, I think.
Thank you so much for the wonderful talk. I'm just wondering that because NA1 has the other drug interaction with the autophase, is there any clinical trial plannings for the thrombectomy with the NA1?
Sorry, I lost
Thrombectomy with
Yes.
the NA1. So you will not going to deal with the drug interactions with the autophase.
Yes, well, their first trial, ENACT, was in surgical patients with aneurysm surgery, so no alteplase, and it worked.
Right.
So,
I mean,
yeah.
I'm talking about the stroke with
Yeah.
the thrombectomy.
Yes.
And then plus NA1.
Yes.
Would that be a possible?
Oh,
in the future
absolutely.
clinical
So
trial?
there are lots of ways of managing this once one understands this problem.
Great, thanks. Dennis, come over here, Dennis. Over here. We have
Oh, sure.
Thank you very much. I promised you that the talks would be exciting. Isn't this just awesome? I mean, really, it's fantastic, and there's more to come. So please, and again, if you need to use a washroom or get something to drink or something, please do that. Anyway, thank you very much for that. The understatement of the year may be that the brain is complicated, and we don't fully understand how it works. One of the most powerful approaches to understanding how cells and molecules in the brain work, however, is to investigate how the genome and genetic expression contribute to function. Likewise, understanding how genetic expression is altered by diseases like stroke has not only become a powerful tool for understanding the nature of disease, but also an important tool for identifying previously unknown processes that can be targeted for therapies. Our next speaker, Dr. Jin-Moo Lee, is an acclaimed researcher who has used genomic analyses in conjunction with neuroimaging and advanced statistical approaches to identify strategies and targets for mitigating brain injury and for enhancing brain repair after injury. Indeed, his approach of using both human clinical studies as well as studies utilizing cellular and animal models of disease has proven to be particularly powerful. Dr. Lee is currently the Norman J. Stupp Professor of Neurology with joint appointments in radiology and biomedical engineering at Washington University School of Medicine. You can see from Dr. Lee's bio in your program that he is highly accomplished and decorated as a physician scientist, and even comes to us with Cornell credibility, having received his MD and PhD in neuroscience from Weill Cornell Medicine. Would you please join me in welcoming Dr. Lee for his presentation entitled From Bedside to Bench, Using Genomics to Identify Drug Targets for Acute Ischemic Stroke. Dr. Lee.
It's a real honor to be here today, to be part of this McDowell Symposium, and to share the platform with so many distinguished guests. And in particular, I'm very pleased that I'm sharing the platform with my former mentor, Dr. Dennis Choi, who I originally came to Washington University to be part of his team, convinced that I would be part of the team that developed the first neuroprotective agent for the treatment of acute ischemic stroke. Now, 23 years later, we're still waiting for that magic drug, but I have not lost faith. And I'm hoping that I can convince you, based on the data that I'll present, that this is an approach that's amenable in human stroke, with the first evidence that I think shows that it is important in human acute ischemic stroke. So I'm going to start off with taking off where Dennis talked a little bit about. So as we know, the field of stroke neuroprotection has undergone a tremendous amount of introspection. So over the last 30 years, there have been over 100 phase 2 or phase 3 clinical trials testing different types of neuroprotective agents. Maybe 60 or 70 different neuroprotective targets have been tested, and virtually none of these clinical trials has been positive. And this has made a tremendously negative impact on the pharmaceutical industry, and there's very little interest in neuroprotection in big pharma as a target for ischemic stroke. Now, there's some increasing interest in the setting of reperfusion. We've heard about thrombolysis, thrombectomy, and in that setting, there's some renewed interest in approaching some of these strategies of neuroprotection. This is a table from a review article that I wrote with Dennis back in 1999. And this is just a small list of some of the different agents that were being tested at the time, the different trials that were ongoing. And you can see even here in 1999, I think the writing was on the wall. We had many trials that showed no efficacy, many that were being abandoned because of futility. And if we fast forward a decade or two, we're still in the same position where all of these trials have been negative, though there's some promise. So why did these clinical trials fail? Well, this failure caused a lot of introspection in the field. A lot of people said, what's wrong with our animal models? What's wrong with the clinical trials that we're doing? And so I've summarized here very simplistically 2 perspectives. One perspective comes from the animal modelers, the people in basic science like myself. We felt that the clinical trials back then were poorly designed. The treatment windows that were used were way too long. As Dennis mentioned, these drugs are effective mainly within the first few hours in animal models. A lot of these trials did not reach the efficacious drug doses that were required for it to be effective when translated from animals to humans. And a lot of this limitation was because of the side effects that were prevalent. And there was also no evidence that the drug targets in the brain of humans was engaged. And that's so important when you do clinical trials to ensure that the strategy that you're coming up with is working so that you can truly test whether it works or not in humans.
And then finally, the endpoints that were used in rat studies were not aligned with the endpoints used in humans. On the other hand, you had the viewpoint of the clinical trialist who thought that animal models of stroke were irrelevant to human disease. As you heard from Dennis, the brains in the rats and the mice are very different from brains in humans. They're smooth, lissencephalic brains as opposed to the gyral brains of humans. And so there was a large group of individuals who felt that the biology of a rat, and as you saw, we can cure stroke in a rat, but it's not working in humans. And so there was a lot of question about whether these rodent models were relevant to human stroke. So all of this has made many of us re-examine our approach to science. So the traditional approach to drug discovery is to start off with a hypothesis, which you test in cell culture and animal models. And then when you find targets that are particularly promising, you translate them into clinical trials. So the problem is that we have identified, it's been estimated, more than 1,000 targets that have been effective in cell culture and animal models, and yet we're only able to translate about 60 of them into clinical trials. And the reason is the cost of clinical trials is incredibly imposing. It costs between $20 and $200 million. And so we can't take 1,000 targets and try them in clinical trials. We need a better way to identify the most promising drug targets. And so the proposal that I'd like to forward is that let's look at science in the reverse direction. Let's reverse translate. So take patients or the bedside, examine the natural genetic variation within human populations, and determine if any of these genetic variants correlate with outcomes after stroke in humans. This makes it very relevant to human biology. And then we take those variants, bring them back to animal models, and determine what the mechanisms are so that we can more rationally approach drug targets. And then we identify these drug targets that are particularly relevant to human disease. I'm not alone in this thinking. Big Pharma has already bought into this in a big way. And what I'm showing you here are titles from two publications, one from AstraZeneca, the other from GlaxoSmithKline, GSK. And when they look back at their drug pipelines, they found that drugs are twice as likely to reach FDA approval if the targets were confirmed with human genetic studies. And so Big Pharma has invested heavily in human genetics so that they can get any lead that they can to identify those promising drug targets. And so we wanted to take a similar approach for acute ischemic stroke. We wanted to use genomics to try to help guide us towards potential drug targets. Now, one of the challenges was to find a clinical measure that could be used to identify these genetic variants that influence brain injury mechanisms after stroke. But back when we thought about this about 10 years ago, my colleagues and I started with the premise that genetic variants may alter early outcomes after stroke, and if we could capture that early outcome, then we might be able to utilize genomic approaches to really get at those targets in an unbiased way. And so the idea would be that those individuals with beneficial genetic variants will have better early outcomes compared to those with detrimental genetic variants. And so we turned to a very common measure of stroke deficit right after stroke, the Nih Stroke Scale, which you heard from already from Dr. Fink's talk. And what we did was we looked at the Nih Stroke Scale upon arrival to the hospital at a very early stage, within 6 hours of stroke onset. And then we measured that exact same scale 24 hours later, because what we wanted to determine were patients that deteriorated within that first 24 hours or patients that improved within those first 24 hours, so we can capture the change in their neurological deficits. And so we called this phenotype Delta Nih Stroke Scale, the change in the deficits between the first 6 hours and the first 24 hours. So those with a positive delta and Nih Stroke Scale were those who improved. Those with a negative were those who deteriorated. And so this became a very important phenotype for us in our genomic study. And so that was the basis of our study that we called Genesis, the genetics of early neurological instability after ischemic stroke. The hypothesis of this study was that this clinical measure, delta and Nih Stroke Scale, could be used in a genome-wide association study to identify genetic variants that are important for stroke-induced brain injury. This started off as a collaboration between Washington University and Vall d'Hebron Hospital in Barcelona, Spain, supported by the NIH. As I said, it started off with this collaboration. We then joined the International Stroke Genetics Consortium, a very large international consortium of stroke neurologists interested in human genetics. And then within 2 years, we recruited 21 sites from throughout the world in 4 continents, from North America, Central, South America, Europe, Asia, all throughout the world, with individual sites that were very interested in stroke genetics. Our patient selection criteria were very simple. We wanted to include ischemic stroke patients. They had to arrive in the hospital within 6 hours of stroke onset with a measurable neurological deficit. We included patients treated with TPA or not. We excluded patients who were non-ischemic strokes. We also excluded patients who were treated with endovascular intervention. Most of this study was done prior to the endovascular era that started around 2015. So we were able to accrue almost 6,000 patients within a 5-year period. These are just some of the demographics of this patient population. Their Nih Stroke Scale was 8. This is a moderate severity of stroke. The average change in Nih Stroke Scale was about 2.5. This went in both directions. And the delta Nih Stroke Scale approximated a normal distribution. So it was very convenient statistically for our analyses. So again, the premise here is that individuals with different genetic variants might have different outcomes after a stroke. And so we were looking for these genetic variants that result in different outcomes. And we accounted for the initial stroke severity based on the baseline, and that's why we used the change in Nih Stroke Scale over the first 24 hours. So just to walk you through a little bit of how we did this genome-wide association study. So we took a population of individuals and we focused on those who had a stroke. And then what we did was we quantified that delta Nih Stroke Scale for each individual. So which ones improved, which ones deteriorated. And then we genotyped each individual using gene chips. So these advanced gene chips today can track about 5 million genetic markers throughout the genome, 25,000 genes. And the idea is we took each of these variants and we were looking to see if there was a correlation between the delta Nih Stroke Scale and the gene dosage of that particular SNP. And then what we looked for was a linear relationship between the gene dose, and that gave us a p-value, a statistical value that allowed us to determine whether there was a significant correlation. And so from there, we can create what's called a Manhattan plot. And all of you are close to New York, so you know why that looks like a Manhattan plot. Essentially, each color represents a different chromosome. Each dot represents a genetic variant, and the value that you're seeing on the Y value is the p-value. And so because we're comparing so many genetic variants, we have to correct for multiple test correction. And so the p-value threshold that we use is a very strict p-value, in this case, 5 × 10⁻⁸. So these are very, very highly correlated values that are being used. And so we performed that GWAS on our delta Nih Stroke Scale in our 6,000 patients, and this is what our Manhattan plot looked like. Now you'll notice that in this case we're using Bayesian statistics, and for reasons that I don't want to get into, but I'd be glad to talk about afterwards, we used this approach. The red line represents genome-wide significance, and what we found were 6 genome-wide associated loci in the genome on chromosome 2, 4, 5, 6, and 7. I want to focus on two of these because I think these are particularly interesting in light of the discussion that we had today. One on chromosome 2 and one on chromosome 5. And what I'm going to do is I'm going to kind of blow up that small region of the chromosome in which these hits fall. So I'll start off with a hit on chromosome 2. So what you see in the colored dots, this again are the p-values that are associated with each of the genetic variants, and you can see they form a very nice peak, which is a signal that somewhere along this part of the chromosome, there's likely a gene or some regulatory element that is affecting the delta and Nih Stroke Scale, that improvement or deterioration. On the bottom, you see a list of the different genes within that small segment of the chromosome, and you find that most of these genetic variants fall within a gene called ADAM23, and you can see that in the red square on the bottom. So what do we know about ADAM23? It's part of the ADAM family of proteins. ADAM stands for a disintegrin and metalloproteinase. These are transmembrane proteins that are involved in cell adhesion or proteolysis. ADAM23 is one of the proteins in this class of proteins. It's expressed in the brain, we know that, and it's involved in cell-cell interactions. And in fact, it's found in synapses of the brain. So the synapse is the part of the neuron, the nerve cells in the brain, where the communication occurs between two neurons. And it's a really important part. This is a cartoon of a synapse, and you can see labeled in green is ADAM23. It's a transmembrane protein that links the presynaptic membrane with the postsynaptic membrane, and it's linked through a protein called LGI1. And this is a very interesting protein complex because mutations or manipulations of various of these proteins can lead to all kinds of different, or not all kinds, but neurological disorders that are related to hyperexcitability. So a mutation in ADAM23 in dogs causes epilepsy. Mutations in LGI1, which is the binding partner, leads to hyperexcitability in a genetic disorder called ADPEAF, which is autosomal dominant partial epilepsy and auditory features, again related to hyperexcitability. And then finally, there's an autoimmune disorder that can develop where autoantibodies develop against LGI1, which leads to a disorder called limbic encephalitis. And this also comes with seizures and encephalopathy. So all of these diseases point to an important regulatory role of this protein in synaptic excitability. So keep that in mind as I move on to the next genome-wide association, which is on chromosome 5. So again, this is a zoom locus plot. We're focused in on a small segment of chromosome 5, and you can see the colored dots line up on top of another gene called GRIA1. And it turns out that GRIA1 codes for the protein, the Ampa receptor subtype 1. This is a glutamate receptor. Now, we heard from Dr. Choi earlier today about an NMDA subclass of glutamate receptors. This is another class of glutamate receptors. So again, Ampa receptors also exist in the synapse, in the postsynaptic membrane. It's a receptor for glutamate, as I said, and it gates the entry of sodium and calcium into the neurons. And it's also a very important modulator of synaptic excitability. And I'm going to show you this exact same cartoon that comes from a review article. And you can see the AMPA receptor is part of this protein complex that links ADAM23 to PSD95 to this gated ion channel receptor, glutamate receptor. So I just want to pause here and just think about this for a second, because this is an unbiased approach. We came to this GWAS with no hypothesis other than that we would find certain variants that would influence outcome after stroke. But out of the 25,000 genes that we surveyed, 2 of the top hits fall within synapses and regulate synaptic excitability. So if there were not more compelling evidence, this is, in my opinion, very strong evidence that excitotoxicity is relevant to human ischemic stroke. As you've heard today, there's lots of preclinical data supporting this. but we haven't made that leap to human studies through the clinical trials for all of the reasons that we talked about. So this is the first human genetic evidence that excitotoxicity is relevant to ischemic stroke, and I think this forces us to rethink this strategy. Now, these are just two of the hits. As I said, we have 6 of them, and some of these other genes fall in other interesting areas of the chromosome. So the one to the top left is PDE11A. This is a molecule that's known to play an important role in learning and memory. There's another hit, PARC2. This is a gene that is known to play a role in familial Parkinson's disease. So another gene that plays some role in CNS disorders. And then the final hit that we have identified here is ABCB5, which is a very important gene involved in drug resistance. It's a transport molecule in the membrane. And then finally, the 6th hit is in a gene poor region of the chromosome, so it's not associated with any particular gene, but it's likely playing some regulatory role in modulating gene expression somewhere else on the chromosome. So I show you these because these are molecules that we're not clear about how they're related to ischemic stroke, but these are novel potential targets that we can bring back to animal models and explore mechanisms further. So this is an approach that we can use to discover potentially novel targets. I want to summarize with the Genesis study. A GWAS of close to 6,000 patients has identified 6 loci with genome-wide association to early outcomes after stroke. Many of these are plausible genes involved in ischemic brain injury, 2 genes possibly related to excitotoxicity, and then there are several other loci with unknown function. But I think importantly, this is a proof of concept that we can utilize these phenotypes of early outcomes after stroke as a clinical measure to study the genetics of ischemic stroke. So on the scale of genome-wide association studies, 6,000 patients is a minuscule study. Most GWASs reach numbers of 30,000 to 100,000, and so we're just beginning to scratch the surface of the potential of this approach, I believe. And so where do we go from here? So I think it's really important that we have fluid flow in the forward and reverse translational direction. We need to be guided by human studies. We also need animal models to help us understand mechanisms. So in that vein, where we're going with this is we're now going to take some of these genes that we've found. We're going to manipulate them in mice through powerful genetic techniques. And in particular, we've already started to overexpress ADAM23 in excitatory neurons and inhibitory neurons. And we're going to test them in animal models of stroke to see if it truly has an impact and understand further what the mechanism is involved. At the same time, we're looking to expand our genomic studies. So 6,000 is a small number. We want to expand that much larger to 10,000, to 20,000 patients. Stroke is a very common disorder. There are 800,000 strokes a year in the United States. So reaching those numbers is realistic. We do need some very simple phenotypes that are standard so that we can reach these large numbers, but we can expand our phenotypes. We focused on one, which was delta and Gnt Stroke Scale. We can look at long-term recovery. We can look at imaging. We can look at penumbral imaging, a collateral flow, edema formation. These are all very important complications of stroke that probably have some genetic influence, and this will allow us to identify potential drug targets for us to go after. And so with that, I want to conclude and thank the large number of collaborators that it took to do this study. In addition to the funding mechanisms through NIH, we got some additional funding through Biogen to help defray some of the costs of the genotyping. And with that, I'd be glad to take any questions. Thank you very much for your attention.
Thank you very much for this beautiful talk. I will say that the last 2 talks have made me very happy because finally in this extraordinarily important field, we're beginning to think of drug combinations, which, because everybody mentioned the brain is so complicated and so complex, drug combinations are almost inevitable. And that was very clear from Dr. Choi's presentation. And the other is, of course, the fact that finally genomics is coming into this game. But I would say that GWAS has its problems in this respect. And that is because with the kind of trauma that impacts the cells very quickly, there are many non-gene factors that get expressed and released. And they may be the causative components rather than the correlative components, which genes always are. I mean, a large number of these genes that one finds connected to something are there, but they're, in a sense, they can be innocent bystanders, I'm sure you realize. So these are wonderful beginnings, but we need to do this with the most advanced tools, as I'm sure you're going to apply, and look at also non-coding regions, microRNAs that are immediately released and which can change significantly the fate of the cell. Just the idea of apoptosis, for example, which Dr. Choi discussed, tells us that there are factors that are not genetics, but released from the genome that might impact this. So congratulations. I think this is on a very, very good road, and I'm very excited to hear more about this. Thank you.
Well, thank you very much for that comment. And I agree with you that one needs to interpret GWAS with caution. The genes are merely kind of a shadow of the complex condition that we're trying to study. I think genomics is just the tip of the iceberg. Is this being shown? Okay, great. So our GWAS only revealed 6 hits, 2 of which were related. But what we're really interested in doing is combining this with other big data techniques, proteomics, transcriptomics, metabolomics. And this gives us a much fuller view of the pathways that are involved. So using these multi-omic approaches, we'll really begin to get into these pathways from which ultimately the drug targets will be derived. But you're right, we do have to translate this back into animal models to truly understand the mechanisms. So I think GWAS is a powerful technique, but it has to be used in combination with many others. Thank you for that comment.
Anybody else?
More questions?
Oh, Raj, here you go.
So just to amplify Harel's thoughtful comments, I notice epigenomics are not on there because I think one of the implications, and I think this has been our bias, is that you're going to capture the environmental influences on the genome through epigenomic changes. And it looks like you probably have what you need to actually do those analyses at this point.
Absolutely. And
because it may give you insight into how the genome is actually changing and how it interfaces with the massive environmental changes that are occurring after stroke.
Right. So there's an advantage and disadvantage to epigenomics. So the genome is fixed since birth. And so we can start with that assumption. The epigenome changes, as you know, with many different conditions, including stroke. So stroke will most definitely affect the epigenome. That will evolve over time. And so capturing that as part of the picture is complicated by that anchoring to the time of stroke onset. And so to truly understand epigenome or even transcriptome, we need to understand its effect over time caused by stroke.
And I guess the other quick question is, does your GWAS allow you to predict whether it's gain of function or loss of function of these particular genes that
Yeah.
is leading to resilience or vulnerability?
I didn't have time in my talk to talk about that, absolutely. So using informatics, I'm just going to skip over some of this. What we can do is use EQTLs to determine which genetic variants alter the messenger RNA levels of the different gene products. And so we can correlate particular variants to levels. And so I didn't have time to go through this, but we did find in the GTEx portal that the chromosome 2 variant altered ADAM23 levels in various tissues throughout the body. So an increase in levels of ADAM23 was associated with better outcomes. So whether that's a gain of function or whether that's a loss of function, the net effect was improvement in outcomes. So. Okay. Sure. Thank you. Great. Thanks. Thank you.
Thank you, Dr. Lee. That was fantastic, really. I mean, the sun is coming out, and I can see people starting to loosen their clothing and so forth. That's just prophetic, because I want to echo what I heard from Harel and Raj here, that there is more than just hope for stroke. There's some real opportunity here, and I'm so pleased to see this unbiased approach yielding to show us that excitotoxicity is another target. We heard a great talk about that earlier. So there is more than just hope for stroke. I think that's the bottom line here. So anyway, thank you. Neurons are not islands, and the major way they interact with each other to produce a remarkable function of the nervous system is through synaptic contacts. Synapses enable physical and chemical information, synapses enable physical and chemical interactions between cells and the formation of circuits to process information, which support neural activity and enables the nervous system to adapt and learn. Among the numerous consequences of stroke is the loss of synaptic function and circuit activity, and the restoration of these processes will be imperative for recovery of function. Our next speaker, Dr. Takuya Takahashi, has a long and accomplished record of investigating how neural activity influences interactions between glutamate, we've heard about this earlier, one of the most prominent neurotransmitters in the brain, and its receptors at synapses to enable the nervous system to function and learn. He has built on this work to develop drugs that guide the positioning of glutamate receptors in synapses, which enables improved synaptic function and accelerates recovery after neural damage. Dr. Takahashi is currently professor of physiology in the Graduate School of Medicine at Yokohama City University in Japan. He has published seminal research in the highest impact journals, many of those, which is a testament to how well his work is received. It is also exceptional that Dr. Takahashi's basic research has formed the basis of a new framework for diagnosing and treating neurological diseases in general, and has provided a promising treatment for stroke, specifically. Would you please join me in welcoming Dr. Takahashi for his presentation entitled Synaptic Plasticity as a Target for Stroke Recovery, From Lab Bench to Human Bedside. Dr. Takahashi will be joining us remotely, I believe, and his talk will be on the screen. So please welcome him.
Thank you very much. It's a great honor to be invited to this symposium. My name is Takuya Takahashi from Yokohama City University. The title of today's talk is Translational Medicine of Glutamate Ampa Receptor. So stroke induces lifelong disabilities such as paralysis, communication disability, and cognitive decline. And also the stroke is a leading disease taking away healthy times globally. There are some stroke rehabilitation methods in clinical practice. For example, the basic one is physical exercise and some challenging technological assistance such as robot and also mental and cognitive therapy, and some experimental therapy. But at this point, at present, there are a few pharmacological approach in stroke rehabilitation. So if we have that kind of drug to accelerate rehabilitation, that would be great. So the concept of this drug is to, by combining rehabilitation with the acceleration drug, induces enhanced recovery after stroke, and ultimately leads to the full recovery. So let me just introduce you the concept of neuroplasticity. Neuroplasticity is the ability of neural networks in the brain to change through reorganization. So if we experience new things or learn new things, so some that kind of a input leads to the circuit changes in the brain. That is just called neuroplasticity. And neuroplasticity is very important for the normal development, learning and memory, and also the recovery from the brain damage. So this is the neural basis of rehabilitation. So if we get brain damage and if we lose some ability, such as some motor functions, we receive the rehabilitation. And in some cases, function get recovered. So in that recovery process, functional reorganization in the intact brain regions occurs through neuroplasticity, and then that leads to the recovery. So, for example, if that brain region is damaged and this region is responsible for moving the right arm, we can move the right arm. But in the process of the recovery by rehabilitation, some kind of a reorganization in the intact brain region occurs and to generate a new circuit to move the right arm, for example. Then in that case, we can regain the ability to move the right arm. So here's the concept of drug to accelerate rehabilitation. So if we can pharmacologically enhance the neuroplasticity in this region, that can lead to the functional reorganization and leading to the acceleration of the recovery. So the facilitation of plasticity could be the basis of the pharmacological rehabilitation. So how can we facilitate plasticity? So we focus on the structure called synapses. So synapses is a structural unit which convey information from the neuron, one neuron to the other neurons. This is the cartoon of synapses. Among various synapses, glutamate synapses are major excitatory synapses in the brain. And the Ampa receptor is a glutamate receptors, and enormous preclinical studies has shown that Ampa receptor is a fundamental component of neurotransmission. Also, the Ampa receptor is a central mediator of neuron functions. This is a cartoon of glutamate synapses, and upon the stimulation of presynaptic terminal, glutamate is released from the presynaptic terminal into the synaptic cleft and binds to the Ampa receptor at the postsynaptic site. The Ampa receptor forms the ion channels, and the cation gets into the synaptic site upon the binding of the glutamate, and that deporizes the postsynaptic membranes. That why it is called excitatory synapses. There are a large body of basic science in Ampa receptors, but its translational approach to understand human disease and to develop diagnostics and therapeutics has been quite limited. So I'm just tell you what is going on the Ampa receptor at the synapses during the neuroplasticity. So during the neuroplasticity, the same kind of plastic event is happening at the synapses. It's called synaptic plasticity. And when we learn, animal learn, or we learn or experience new thing, brain can change. That's, as I told you, that's called neuroplasticity. During this process, Ampa receptor get inserted into synapses, and the number of Ampa receptor at the synapses is increased, and the synaptic transmission is changed, increased. That is the basis of the synaptic plasticity, and it's called experience-dependent Ampa receptor trafficking. So about 20 years ago, I first found that experience drives Ampa receptor into synapses in the living animals. So to prove that, we use the whisker barrel cortex system. Barrel cortex is a cortical area which receives sensory input from whiskers. So there exists a barrel column like this, and there exists a very nice topographic mapping between each whisker and the barrels. And that topographic mapping is established in the first 2 weeks after birth. So during this period, I found that whisker experience drives Ampa receptor into synapses. However, if in the adult animals, when the barrel cortex has already been matured, natural whisker experience no longer drives Ampa receptor into synapses. We use this system to identify a novel compound to facilitate synaptic Ampa receptor delivery. That compound is called adrenergic malate. So using adult barrel cortex, we first administered this drug to the animals in the adult, and we cut acute brain slices, including barrel cortex, and recorded synaptic transmission from layer 4 to layer 2-3 pyramidal neurons. And the y-axis shows Ampa to NMDA ratio. NMDA receptor is another glutamate receptors. That just simply saying the y-axis shows the Ampa receptor trafficking. So the number is high. That means more Ampa receptor get inserted into synapses. So the animals treated with the drug showed the increased Ampa to NMDA ratio compared to the vehicle treated animals. So that means this drug drives Ampa receptor into synapses. And this process is not a constitutive process, because if we trim whiskers, animals with a drug treatment didn't show the increased Ampa to NMDA ratio compared to vehicle treated animals. That means this drug facilitates experience-dependent synaptic Ampa receptor delivery. So just simply saying, adrenergic malate is a synaptic plasticity enhancer. So does this drug accelerate motor functional recovery after brain damage or not? To test that, we use reaching test to evaluate bluntly foreign movement in mice. We put a treat in front of the mice and train them to pick it up. So since this is a very little bit difficult task, so success rate is low at the first, but as the training goes, the success rate goes up. After that, we introduce cryogenic injury in the motor cortex, and then success rate gets down to the basal level here. So we applied drugs to these animals. This is the success rate before introduction to the injury, and this is after the introduction to the injury. So the animal with a red line shows a prominent recovery, and in this animal, we treated the animal with a drug in combination with the training. Since this injury is very large, just water application didn't induce the recovery, even with the training. Quite interestingly, if we treat animal with a drug without the training, this animal failed to recover. So that means drug accelerate motor functional recovery in a training dependent manner. So this is consistent with the idea of the synaptic plasticity, in which the specific input into the specific synapses changes the synaptic responses at these synapses. So in this process, the synapses used in the training is changed more easily than with the drug than without the drug. So that induces training, functional recovery in a training dependent manner. So that drug carries the idea of synaptic plasticity. This is the first drug with this concept. So this drug binds to the molecule called CRIMP2, and CRIMP2 is called collapsin response mediated protein 2. This has been identified. This is a molecule first identified as the downstream molecule of semaphorin signaling. Semaphorin is initially identified as the molecule which control the growing axons during development. But now some studies have shown that semaphorin and CRIMP2 is involved in the plasticity event. So that's a quite interesting molecular target of the drug. So if we use CRIMP2 knockout mice, which lacks a CRIMP2, and did the same experiment with the drug. So we introduce the cryogenic injury and applied drugs to CRIMP2 knockout mice. As you can see here, the CRIMP2 knockout mice failed to recover with the drug. So that means that the binding of the effect of the drug is mediated by the binding of this drug to CRIMP2. So there's a huge species gap between the rodent and human. And so to test if this drug is effective in primate, we use non-human primate, macaque monkey. So we introduce internal capsule hemorrhage. So to test if drug recovered these monkeys, we use the two different distinct tasks. The one is horizontal reaching task. In this task, we put a treat in front of the monkey. So monkey picked the treat up. So we measure the time to retrievals. If this time is short, that means the quicker quicker retrievals, and that means the better recovery. The other one is grasping task. In this task, we put the treat in the acro pipe so that monkey has to pick up this treat using index finger and thumb. So they need the dexterity of the fingers, then that is important for the ADL. So this is the data of reaching task, and the y-axis shows the recovery rate. So the number is high, that means more recovery. So red line shows the recovery of the monkey treated with Edmund maliate, and the black dot is vehicle-treated animals. As you can see here, pretty good enhanced recovery with the drug compared to the vehicle. So let me show you the videos here. This is water-treated pre-training animals. Actually, it's quite slow. The finger movement is pretty lazy. So right side one is water-treated 2 weeks of training. This basically, it's the same. It's a slow, and it's not really good recovery here. Yeah, and this is drug treated. This is pre-training and pre-administration of the drug. Actually, this monkey shows more severe phenotype. So it looks much slower than the previous one here. Yeah, it looks hard to pick this up for this monkey. And this one is the post-training with the drug, 2 weeks of training. It's much faster here. So it gets recovered pretty well. So the other task, it's a grasping task. Y-axis shows just success rate. In this task, again, monkey has to pick the treat up using index finger and thumb. So in this task, actually, we show the more robust results. And in the Edmund maliate treated monkey shows the 90% of success rate with the trial, but vehicle treated animals shows only a few percent of the successful trial. So this is again video here. This is the water-treated pre-training animals. This is actually a very tough task. It's a failure. This task is failure. So this is 1 month of training with the water. They're not much different. It's again failure trial. And this is drug treated. This is before training. Again, the same. It's a failure trial here. And this one is post-training with the 1 month of training with the drug. So it's just much better. So, this drug, adrenergic malaria, can be the first small compound as a rehabilitation enhancer after stroke, and now clinical trial to test the efficacy of adrenergic malaria for stroke patient is now ongoing. So let me just tell you one more story, one more thing. So actually the bottleneck in the stroke recovery field is the lack of biomarker for functional recovery. So we have a lot of options for the rehabilitation, but we can't really optimize the method due to the lack of this biomarker. So it is very important to evaluate the effect of the drug using the kind of biomarkers. So again, back to the cartoon with synapses, and Ampa Receptor is well characterized in animal studies, but as I told you, translational approach of Ampa Receptor biology has been limited. The big reason is that until recently, there is no technology to visualize Ampa receptors in living human brain. So we have recently developed the first technology to visualize and quantify Ampa receptor in the living human brain. It's a PET tracer, and new to PET tracer called carbon-11K2. This is the first in human test. It's the first image of the Ampa receptor in living human brain, some accumulation of frontal cortex, and some accumulation of the cerebellum. So we scanned the patient with the stroke with this PET probe, and this is the before the one. This is a patient with the infarction here, and this is a PET image before the 1 month of rehabilitation. This is after the 1 month of rehabilitation. We subtract the PET image in the at the first scan from the second scan, and we can see some Ampa receptor accumulation in the motor cortex during this 1 month of rehabilitation. So we scanned 6 stroke patients, and these left two patients shows prominent recovery, and you can see good accumulation of Ampa receptor in the cortex, including motor cortex. But these 4 patients showed poor recovery and poor accumulation of Ampa receptors. So that implied that carbon-11K2 can be a biomarker for functional recovery. And now the carbon-11K2 is used in the clinical trial of the adrenergic malaria for stroke patients. So the final is acknowledgement. These are the member of the lab member of my lab, and Hiroki Abe and Waki Nakajima developed the rehabilitation drug, and Tomoki Miyazaki developed the PET tracer. These are the collaborators, and these are the fundings. Thank you very much.
You must be tired.
I'm okay.
That is fantastic. I just love the travel from basic to clinical work. It's just it's a tour de force. There must be questions. Please. There's a question here.
Very nice talk. Thank you so much. I was wondering, towards the end, like the last slide, the patients that had accumulation of AMPA, was there any seizure activity detected after a stroke in these patients?
Well, that's a very good question. And unfortunately, these patients we scanned didn't really show the, post-stroke epilepsy. But that is, I think, a very important issue, because we scan actually a lot of patient with epilepsy, and we observe accumulation of Ampa receptors in epileptic focus. That means, hyperexcitability induced by the accumulation of Ampa receptor, can cause some epilepsy. So during the course of the recovery process after the stroke, that must be controlled. So we'll see what's going to happen with the clinical trial of this maleate, and we hope they can, prevent epileptic seizure as well as the recovery from the stroke. Thank you very much for your question.
Right.
Okay. Great, Takuya. Thank you for an amazing talk. Every time I hear the story, I get more excited.
Thank you.
The robustness of your effects raises the possibility that actually this collapsin response mediator protein is involved in many aspects of repair rather than simply only Ampa receptors. Have you begun to explore, taking you back to your strip motor roots, effects like on axon outgrowth or other parameters that we associate with repair?
Wow. Thank you very much for your question. You must know my history, right? Yes, actually, we did try to see some, axonal, changes such as increased collateral or something in the rat or mice. We didn't really see a difference as far as we, observed. But, I think, you're right. I mean, CRIMP2 should have a lot of, effect, not only to the Ampa receptor trafficking, but also to some morphology such as spine, morphology, and also axonal, morphological changes. So I think, that should be thoroughly, observed or, investigated in a later study. But yeah, that's a good question. And yeah, thank you very much for your question.
Are there any other questions? Oh, yeah.
Congratulations on that work. That's truly remarkable. And in earlier discussion today, we talked about the importance of excitability-inhibition ratio, having reverse effects acutely versus long-term. And I'm wondering if you can tell us a little bit about the design of your clinical trial towards that end, in terms of when you would start something like this and what the coupling between your drug and rehab might look like.
Yeah, I think that contains a couple of questions. One is EI balances, excitability inhibitory balances issues, and actually it's the very interesting question, and our preliminary results show that in the animal experiment, the naturally recovered animals without drugs shows some increase of excitatory synapses, synaptic functions, but inhibitory synapses stay in the same amplitude. So, but if we add drugs to these animals, and that enhances both excitatory and inhibitory synapses. So EI balance issue is, I think it's throughout the recovery is pretty critical issue, and looks like this drug enhances both Ampa receptor trafficking and GABA receptor trafficking, and balances that EI balances. And also the second question, this is probably regard to some EI balance issues, but how we design the clinical trial is basically, it's based on the animal experiment we performed. That is acute to subacute phase. So we screen the patient, which is the severity and some other stuff is fit for clinical trial. We start, administration of the drug, let's see, 1 month after the incident or something, and then you just to keep it going for 3 months, and how the drug works. So that is acute to subacute phase, and the one big issue is whether that drug is effective for the patient with the chronic stage. And we actually did some preclinical study using the chronic animal, like 4 months after the incident, the injury. That works, but it's I would say it's just a little bit less than the acute phase. So there are a lot of issues to be solved, and that includes your question, how it works at the chronic stage. And thank you for your question.
Great, and one last question.
Yeah, thank you very much for the really very exciting work. I had my question was about your Ampa probe with the PET scan, which is really exciting. I was wondering, when you showed the data that, with the training and in some of those patients where there was an increase in that activity or accumulation in the motor cortex, I was wondering if you could also look at it in the converse. In other words, to get recovery, do certain circuits have to go offline? Would you be able to see that if there's not trafficking, that might also be meaningful for the plasticity? And have you looked at that?
That is, good question too. So we only just show the increased Ampa receptor signals in the brain after the rehabilitation. But actually, we did observe some brain region with the decreased Ampa receptors. So I skipped many data which we published recently, but this PET probe actually, images the cell surface Ampa receptors. So the accumulation of Ampa receptor, I said accumulation of Ampa receptors, but I say that the trafficking Ampa receptors. So some brain regions shows the trafficking of Ampa receptors in response during the process of recovery, but we did see the decrease of the surface Ampa receptor as well. So maybe the LTD-like thing that, as you suggested, is also occurring in the recovering brain, and that is also important for the recovery. Thank you for your question.
Well, thank you, actually, Dr. Takahashi. I mean, it's for your forbearance and so forth. Thank you very much.
So our first awardee is Tedy Bruschi, who is known to many of you. He's a well-known NFL player and broadcaster. I have to say, Elizabeth, that, and don't tell Tedy this, that I'm a lifelong Steeler fan. And so I've suffered the pain of his competence for many years. That other guy who's now playing in Tampa Bay, or we think, or whatever, this is also not high on my list of favorite football players, but the family is, my family is avid football fans, and we've obviously admired him for a long time just for that. But what is the really amazing story is that when he was 31, following a very successful year, actually winning the Super Bowl, going to the Pro Bowl, Tedy suffered a stroke. And this is, I think, was an important event, not only in Tedy's life, but I think in the stroke field's life, because I think we always think of stroke as an age-related disease. That is the #1 risk factor for stroke. But the reality is that stroke affects people across the lifespan. And I think that it is important that we really understand why that happens, create awareness.
Recording in progress.
Yeah. Is that my cue? But I think what was exciting about the fact that Tedy recovered, that he and Heidi actually realized that Tedy's full recovery offered an opportunity to pay things forward, isn't that right? And Tedy's team was set up as a way to create awareness about the fact that stroke can actually affect people in many walks of life, but also then to create fundraising for support for those who might need it, for research, and more than $8.5 million has been raised. And I think all of those things really said to us that his impact on stroke disability, stroke awareness, and as important, I think, his living example of resilience, that not everybody who has a stroke ends up in a wheelchair or is someone who is not able to speak. And I think that's also an important message. So we are really honored, and really honored to have you, Elizabeth, here. I think we'll be hearing from Heidi and Tedy, who couldn't be here in person, but they have a standing invitation to come down and visit anytime. And we have Diana and Vibhu, our great tour guides. There's so much I think they would find exciting in the Institute. But on behalf of the staff, the faculty, and our board, it's really our honor to present Heidi and Tedy Bruschi with a 2022 McDowell Award.
Hi everybody, my name is Tedy, and this is my wife Heidi. We are co-founders of Tedy's Team, a nonprofit we started back in 2005 after I had my first stroke. Tedy's Team raises awareness of stroke and heart disease, funds life-saving research, education and awareness programs, as well as financially supporting survivors, giving them the means for a comeback. We are so sorry we couldn't be with you today, but we want to thank everyone there for your hard work in stroke and research care.
Congratulations to our fellow award winners. We know that we are an amazing company. Lastly, we are honored to receive this award from the Burke Neurological Institute. And we want to thank all of the people who support what we do on a daily basis. Thank you.
Thanks, everybody.
So thank you. I'm not here to say anything about Tedy's Team, as Tedy and Heidi just did that, but I am here. Tedy and Heidi and your staff wanted to give you something special for your 20 years of service to Burke Neurological Institute and stroke research and awareness. And so I have a little something to present to you. I apologize, it's not a Steelers jersey, but this will have to do. This is a signed Tedy Bruschi jersey specifically for you.
All right. Well, my allegiances may have just changed.
And then he put a little message on the back to you as
thanks
well.
So much.
For your 20 years
great.
of service. So thank you so much. Thank you, everyone. Oh, yeah.
So I'll have it.
Yeah. I'll pick up the...
Here, I'll put that in there.
Thank
Thanks.
you.
We definitely have to do these award events more often. I'm definitely the first. Oh, you're next.
The guy gets a shirt and he goes all, and besides, you got to wear that thing now, Raj, for the rest of the day. So, yeah. I have to retool here a bit, but let me tell you, I'm excited about this today because I get the honor of giving an award to two people who I think very, very highly of. First up, right here. Dr. Bernice Grafstein is one of my scientific heroes, truly. And not only because she is a fellow Canadian expat, which she is. We were geeking out on that last night, weren't we? But because of the enormous impact that she has had in the field of neuroscience, her exceptional dedication to teaching, her tireless mentorship of people throughout her career, me included, her wry wit, let me tell you, and self-effacing style is always just under the surface with her, and her seeming ability to defy the space-time continuum itself by doing all this at an age when others have stopped. Whatever she has, I want some of it, and I want it now. Dr. Grafstein is currently the Vincent and Brooke Astor Distinguished Professor of Neuroscience at Weill Cornell Medicine and a member of my department, the Department of Physiology and Biophysics. She has many accolades, and among them is her election last year to the American Academy of Arts and Sciences. To give you a taste of her personality, I love what she said when asked about how she felt about the honor. She responded, "I'm extremely thrilled. I love the fact that this has come at a mature point in my career. I can savor it all the more. I can just hear her dripping sarcasm as she hangs on the word mature." Dr. Grafstein is extremely well known in the field of neuroscience because of her pioneering discoveries about nerve cell damage and regeneration. Her earliest work as a graduate student was related to migraine and stroke, so there is a stroke hook even with her, and is still highly referenced more than 50 years later. I hope we're as lucky as that as scientists. Her reputation, however, was solidified by her subsequent seminal studies on optic nerve regeneration in lower vertebrates, which showed that nerve regrowth after injury was regulated by changes in the nerve cell itself, not necessarily at the site of injury. This is an important concept. This laid the crucial groundwork for subsequent studies into the potential for regeneration in the human nervous system. Her work also provided insight into the process of axonal transport, which moves materials along nerve cells and is critical to their normal function for neural repair, and was co-opted as a technique to trace neural projections. Indeed, Diana Willis, who's there handling the microphone, her work at the BNI certainly flows from Dr. Grafstein's work. In addition, her work on neural preconditioning, a phenomenon in which the nervous system seemingly learns to regenerate better after it has been injured, has formed the biological basis for the concept of resilience, something you've heard about today, which is one of the most promising approaches to prevent and treat the effects of neural injuries like stroke. Dr. Grafstein earned her bachelor's degree at the University of Toronto and a doctorate at McGill University in Montreal. After her postgraduate work at University College London, she held faculty positions at McGill, Rockefeller, and in 1969, she joined the Department of Physiology and Biophysics at Weill Cornell Medicine, where she has been ever since. There, she has been a leader in teaching medical students and graduate students, and has become an important advocate and role model for women scientists. Dr. Grafstein was also the first woman to become president of the Society for Neuroscience, and she sponsors the Society's annual award for mentoring women in neuroscience. And indeed, was at the Society for Neuroscience meeting when Dr. Grafstein was president that I first met her. I was a second-year graduate student and was paralyzed by fear when the president herself came to my poster on a project that I was working on just as a side project. I will always remember her casual style and encouraging words that filled me with confidence, and I'm forever grateful for that. Thank you. And decades later, when I met her again at Weill Cornell during my recruitment, she still remembered me, she still remembered that circumstance, and was just as encouraging. Indeed, you are timeless. Dr. Grafstein, you are an inspiration to all of us at BNI. And on behalf of the Burke Neurological Institute, I would like to present you with the 2022 McDowell Award.
I want to say that I'm particularly thrilled to receive this award in the name of Fletcher McDowell, whom I knew, whom I respected, and whom I really loved. He was a wonderful man, and his warmth and his personal efforts for all around him, I think many of us were very touched by him over the breadth of his career. So he was somebody who was special to me, and I'm really honored to receive this award. Thank you.
That's a hold this and get a picture of it.
Okay.
Come over here a little bit. Fantastic. You may not know this, but before the award, I went to the dictionary and looked up the word competence. And unsurprisingly, there was a picture of Dr. Harel Weinstein, which, by the way, it's impossible to tell when it was taken because I'm sure that at every stage of his career he was competent, but also because he never seems to age. He looks exactly the same as he did when I met him 16 years ago. There are many people who are accomplished scientists, and on this measure, Dr. Weinstein is as good as they come. Evidence of this is that he is the Maxwell Upson Professor of Physiology and Biophysics and the founder and director of the Institute for Computational Biomedicine at Weill Cornell Medicine. He also holds appointments at Rockefeller University and Memorial Sloan Kettering. He is an elected fellow of the Biophysical Society and the American Physiological Society, and has served as the president of the Biophysical Society and the Association of Chairmen of Departments of Physiology, and the International Society for Computational Biology. And of course serves on numerous scientific boards. He has attained these positions because he is an outstanding scientist, no doubt about it. Specifically, an outstanding biophysicist. In biology, there is an adage that structure equals function, and the study of biophysics is where this is most evident. Dr. Weinstein's work has produced seminal insights into the inner workings of the structural and electronic determinants of biological processes using theoretical, computational, and bioinformatical methods. If you want to gain insight into what all that means, just ask him to describe how a sodium ion and water moves across the cell membrane, and expect the explanation to take some time. This work at this detail has consequences, because it is at the root of understanding how biological systems work at all, how they fail in disease conditions, and how they will be repaired to enable treatment. A particularly weighty example of this is Dr. Weinstein's recent work on the mechanisms of how COVID virus interacts with cells, which has provided crucial insights into how to design effective antiviral therapies. He was showing me this morning with some knuckles and so forth, that. Whereas Dr. Weinstein's scientific accomplishments are outstanding, I must say that his administrative abilities are equally, if not more, outstanding. I can't tell you how rare the mix of these qualities is. And it was evident when I was recruited by Dr. Weinstein in his position as chair of the Physiology and Biophysics Department. During that process and since, it is clear to me that he was the best department head that I had ever met, no doubt about it. He not only leads with competence, but is hardworking, exudes fairness, balance, calmness, integrity, wisdom, prudence, and creativity. And he has an uncanny ability to focus on the long game when others are distracted by the present. He is also somehow able to simultaneously focus on the goals of individual students, staff, and faculty, on the goals of his department, and on the goals of the Institute. It is truly remarkable. In addition, he is a polymath. Just ask him in whatever language you want, and he'll probably answer you. And he has an outstanding sense of humor. I owe Dr. Weinstein my gratitude, and I'm very proud to call him my boss. The qualities of outstanding science and outstanding administration have been on full display for the past 15 years that Dr. Weinstein has served as a member of our scientific advisory board. Without question, his service to the BNI has been remarkable. He has brought passion and a sense of purpose to the BNI and has helped steer the Institute according to its mission like no one else. The Institute owes Dr. Weinstein a great debt for his service for the past 15 years, and yes, for your competence. And we are looking forward to you to guide us into an even brighter future. On behalf of the Burke Neurological Institute, I would like to present you with the 2022 McDowell Award.
I'll be very brief because everybody has heard too much today. Of course, I have a sense of humor. I've been on this board for 15 years. That was very helpful. but truly, I enjoyed every moment that I was in touch with this group, not only because of the brilliant scientists that Raj has brought together in this institute, but because of its goals, which are deeply human, deeply humanitarian, and at the same time, fundamentally, rigorously based on science. That is also a very rare finding in an institute of this kind. So I am happy and grateful for having been accepted to participate in this experience. Thank you very much.
Thank you. Oh?
Your eyes
My
were
bad,
closed?
my bad.
The man needs some sleep.
Yeah. All right, thanks. Raj.
All right. Let's see what we got here. All right. Last but maybe most, the Hamiltons. I think I'll take a moment to tell you a little bit about them, and then I'll share some personal perspectives from the Institute. Annie, who's with us today, was diagnosed with Friedreich's ataxia at the age of 9. And are you 17 or 18 now? 17. And she now spends time not only educating different groups but companies about Friedreich's and her personal experience with it. Amy Bialek is here, and she's worked closely with Annie over the past several years in trying to optimize her function, and she's graduating from Sacred Heart, and congratulations going to Notre Dame. Having just gone through this process with my daughter, the college process is a complete institution in and of itself now. It's a full-time job. So congratulations on that remarkable achievement. I will say Notre Dame is not another one of my favorite football teams. But maybe you can change that if you want to get me a jersey. Equally amazing is, so behind this remarkable young woman, and I think we all know about the millennials and the sense of entitlement. Annie is the antithesis of that. She is gracious, she's always polite, and incredibly hard worker. And I think obviously Tom and Karen, you deserve enormous credit for that. But as important, I think, and another reason why we're honoring them is that they've really walked the talk. And I think one of the reasons we selected this family is because we believe that real hope comes from great science. And I think the investments that the Hamilton family has made into the CureFA and other organizations, investments at the Broad to fundamentally understand this disease and really bring benefit for everybody is remarkable. And it's really, I think it's a role model for how we should all be working together, because it really shows that it's not only scientists and clinicians, but it's families who really understand what's going on. So I wanted to finish by saying, Annie, we really miss having you around, because I used to always love walking into the Institute and hearing Taylor Swift, as she was walking down the hall. And the other part of this, which was so important to us, is that, we have many people in the Institute who spend time every day, pushing test tubes, and doing very detailed experiments in cells and in animals. And to be able to see you every day, many of them mentioned to me as they walked in, I think it created purpose and meaning every day to what we do. And I think it's incredibly emotional for me, because I think all of the people who are scientists here really believe that we're on a mission, and people like you inspire us. So don't forget that. It's an incredible honor for us to give Annie, Tom, and Karen Hamilton the 2022 McDowell Award, and I'll come to you. You don't come to us. Okay, yeah. Yeah, okay, great. Oh, yeah.
Thanks so much. We're really honored to be amongst such distinguished company. And I'm not sure we feel like we deserve an award. We're just parents trying to help our kids. We found an amazing group of people here at the Burke, and it's a good story for you as we go through in our journey with a neurological disease. You find yourself, when you're looking for resources, at a lot of stroke and spinal cord clinics, whether you like it or not. We were looking for a robotic suit. We were looking for some work with exoskeletons, and it leads you to places like this. But when we got here, we found out there's a lot more than just that. And the work that everyone here does around neurology and around the biologics of the brain have a lot more impact than just stroke. And I know we're talking about stroke today, and I learned a lot, and it's been fantastic. But it stretches to so many other diseases and so many other things that we can learn together. So we're very honored to be here. I hope you know that you always learn a lot more from the patients than we can give to them. And I've learned more from my daughter than I've ever given to her. And I think all the doctors here, we really appreciate it. We thank you from the bottom of our hearts. And thank you for having us around, and we're honored to accept the award. Thank you.
Thank you.
Congratulations.
Thank you. Thanks, Rob.
Wow, I miss her too. The music Raj brought up was always a treat, so thank you. I truly do miss you because we come in and you're always so happy, and it's just awesome. I'm just so pleased for you guys get the award. There was a bit of technical difficulty earlier, so what we're going to do is just sort of reboot. We're going to go into our combined lunch hour and tour hour right now. And so we'll keep everything on schedule, come back at the time in the program. But those of you who are signed up for tours, where are we meeting? Right
over here by the registration desk.
It's by the registration desk. The rest we can start with the lunch service. Do not worry if you go on the tour. There will be plenty of food when you come back. And I think if we do this right, there should be a time for us to mingle and talk and so forth. And there's more to come. So again, thank you for coming, and enjoy yourself for this lunch hour. Well, let's continue. And what I wanted to do is again remind you of the theme of our symposium today, Hope for Stroke, and how the BNI and other institutions that you're seeing now are engaged in a research effort to reduce stroke vulnerability and to foster resilience. You saw a very provocative talk just now on how basic research is pushing things in that realm toward the clinic. Sorry, this theme then is exceptionally embodied in the work of our next speaker and BNI friend, now certainly Dr. Selva Baltan. Dr. Baltan is a highly accomplished scientist and is currently the endowed professor and vice chair for basic research of anesthesiology and perioperative medicine at Oregon Health and Science University. The focus of her current research is on understanding the mechanisms of how and why white matter is damaged by brain injuries like stroke, with the goal of developing therapeutic procedures to protect white matter and to restore function. This work is of clear clinical importance because unlike the brains of many of the animal models of stroke that have a preponderance of gray matter or cell body regions, the human brain is characterized by an extraordinary abundance of white matter or connections between these gray matter areas. Understanding how this tissue can be protected is critical to improving human stroke outcomes. A particular focus of Dr. Baltan's work is on using preconditioning mechanisms, something we heard about before, as a means to protect the brain. Would you please join me in welcoming Dr. Baltan for her presentation entitled Mechanisms of Stroke Therapy and Prevention. Dr. Baltan.
Good afternoon. First of all, I'd like to thank Dr. Ratan and the whole Burke Institute for inviting me here, and to be among you today is a thrill for me. You have listened to a very interesting talks all morning talking about how stroke injures the neuronal cell bodies, the synaptic transmission, and now I want to take your attention with me to a different portion of the brain, which is called white matter, so that we can take a walk along the axons and glial cells and change our venue from the neuronal aspects of stroke. I'd like to first acknowledge my current and my former team and my collaborators and funding sources for their participation and support in this work throughout the years. Now, you have a great idea of what a stroke is. It's basically the blood vessels provide the oxygen and glucose to the neuronal and glial and axonal elements in the brain, because these are the essential nutrients to drive energy. Brain is very sensitive to lack of energy, and it's a highly active organ in our body and needs a lot of actually the energy produced in our body. Therefore, a continuous supply of oxygen and glucose is necessary. And when there's a clot formation or a rupture in a brain vessel, this circulation and this substrates are interrupted from being provided. And what happens is, due to the lack of nutrients, then the cells will start dying, which causes these white shape, the infarct volume in the brain. Who gets a stroke? What are the risk factors of getting a stroke? There are some simple life conditions that actually makes us prone to get stroke, such as having high glucose levels, having a bad diet, a poor diet, and being obese, overweight, having a very sedentary life, so we don't exercise enough, being a smoker, having a high blood pressure, or having high cholesterol, all makes us prone to have a stroke as an increased risk factor. And you've also heard this morning from Dr. Jin-Moo Lee that some genetic factors also contribute to the risk of having a stroke. And in fact, the latest studies have found that there are 32 different genetic loci that can make you to have a higher risk for developing stroke. What do we do to increase awareness for stroke? American Heart and Stroke Association has been actually very successful. May is the Stroke Awareness Month, and every year they come up with these very catchy abbreviations, such as Be Fast, to educate the public about the signs and symptoms of stroke, such as this one, BFAST stands for loss of balance, loss of eyesight, asymmetry on your face, inability to raise your arms, loss of speech, then it is time to call for help because this could be the signs and symptoms of stroke. Again, as we have listened from Dr. Finn this morning, that stroke is still a very prevalent disease in the United States, about 800 new patients every year. And if you put it to statistics, that means that there is a patient every 40 seconds, and we lose someone from stroke every 4 minutes. In the United States, it's the 5th leading cause of death. It's the 2nd one around the world, but it is the #1 reason of disability in the United States. Very interestingly, about 20% of the major universities, health facilities in the United States are actually certified for taking care of stroke patients. And currently, as you have also heard in the morning, we have 2 interventions that we can offer to these patients. One is TPA, the clot buster. If you are in a hospital environment or in a unit, you have an ambulance for that, then and within the first 4.5 hours after having a stroke, and the clot size is below a certain amount, then you can have TPA and you can have a reinstatement of your circulation. However, only about 7 to 10% of the patients are eligible for this treatment. The remaining group of patients, some of them, will be eligible for thrombectomy, where this thrombus, when the clot is larger than the activity of TPA, then it can be mechanically removed to reinstate the circulation. However, these interventions, although they're only available for a certain group of patients, do not stop the entire injury cascade, because at the onset of the stroke, the injury systems are already activated. So even if you see an immediate recovery, there's the chronic phase of the stroke, which these already onset of these injury mechanisms will take an effect. This is the reason why we, the stroke researchers and clinicians, are still very keen on developing drugs to offer to these patients. And at this point also, as you've heard this morning, this is the time when we throw our hands and say, why do we fail to treat stroke? Because we have had many successful results in our laboratories, but when we took them to the clinical applications, we couldn't repeat those success levels. And looking retrospectively, we drew actually main points that have resulted in our mistakes. And some of them you have also heard during the morning talks, that we had to make sure that we're working on appropriate experimental animals. We have to employ also appropriate stroke models in our studies. We definitely have to set parameters for the outcome measures of which drug is beneficial versus not. And we have to definitely increase our study quality. We have to standardize those between different centers. And we have to be mindful when we're selecting our patients and the dosing regimens of the drugs that we're testing. At this point in time, I was very new at my career and had just graduated from McGill University and joined the group of Dr. Dennis Choi. And Dennis, as being our chair at the time and very well known in excitotoxicity field, I was hoping to work with him on neurons and synapses. But he said he had the vision that the one of the most important parameters that we are not addressing for stroke studies is looking at what happens in white matter. So my career took a great turn, a different trajectory, actually being mentored by Dr. Dennis Choi at that time, and Mark Goldberg and I started with him working on white matter injury. So what is white matter? If we put it into a very simple form, our principal cells in the brain, the neurons, are these like light bulbs. That's where the activity is initiated in the brain. And collectively, let's call these light bulbs as the brain cells, the neurons, but they form the outer aspect of the brain, which is the gray matter. However, this initiated information has to be communicated with the rest of the brain. And for that one, they need to be connected through cables. And these cables are called the axons. If they don't have these cables, the initiation of this information will not be executed. You will not be able to move, you will not be able to talk. So these cables in the brain are called axons, and they're just like electrical cords insulated by a material called myelin, which is white in color. That's why it's called white matter. If you look at this minimized cartoon approach and look at what happens during an ischemia, here is a neuronal cell body with its myelinated axon, let's say in your cortex, and after a stroke, if you offer no protection, then both this neuronal cell body and its myelinated axon will die, and it will be a neuronal and an axonal death. But if we only focus our efforts to protect the neurons, then after a stroke, this neuron can survive for a moment, but if its myelinated axon is dead, in time, this dead axon, through Wallerian degeneration, will retrospectively kill its cell body. So in the long run, there will be not much of a difference between no protection and neuron-only protection. This is the reason why we have to protect both our neurons and their myelinated axons. And if you look at a human brain, you will realize how important this addressing both portions of the brain, because you can see that the gray matter, the neuronal cell bodies, are on the outer edge of our brain, but inside of our brains are filled with white matter. So by volume, 50% of our brain is white matter. And if you look at it in a three-dimensional way, that these axons form actually very intricate, very extensive and established network. And even if there is a very small infarct in a critical area of these white matter, where all the axons are intersecting each other, it could cause that debilitating disability that we observe after a stroke. If you want to take an up-close and personal visit to one of these axons, which we often do by using a three-dimensional electron microscopy, you can see that I think I need someone to help me with my computer. It's not playing my video. Okay, this one has to, the yellow one. Yes. So if you look at an axon, actually you can see that it is a structure, like a tunnel that is connecting from one cell body to the next one. And you can also see what's inside of an axon. In this case, these yellow structures are organelles called mitochondria. Mitochondria are like the batteries. They are the ones actually who take the glucose and oxygen and convert it to an energy so these axons can function and stay alive. And if you look at what happens after an ischemic insult, can we play this movie too, please? The blue one. And you can see that the contours of these axons do change. They become swollen in some parts, very narrow in other parts. But if you look at the organelles, the mitochondria, then you can see that they're extensively damaged. To an extent, actually, that there are only a few of them are left. Therefore, there is a drastic loss of energy production that impairs the function and viability of these structures. We have also developed other modes of looking at the axons by generating transgenic animals, because we also wanted to watch the function and activity of these axons live in a live mode. So in a transgenic animal that we have generated, you can see the neuronal cell bodies in red as hollow structures on the upper left corner, and you can see the red connecting axons there. And all these fluorescent, cyan fluorescent structures are actually mitochondria, and we can watch them actually move during physiological control time and during a stroke and after a stroke. And using these transgenic animals, we have determined that in a control condition, you can see a lot of these fluorescent mitochondria in the white matter. But after a stroke, there's a drastic loss of this fluorescence, which correlates to loss of and damage of these mitochondria, which I have already shown you. If we block this stroke injury by using an Ampa receptor blocker, MBQX, then we can preserve these mitochondria. You've heard about excitotoxicity this morning and also the role of Ampa receptors. So there's a way to protect these mitochondria, which is also good news because if you look at this preservation, their good-looking shapes is also correlated with their function that they can produce as much ATP before injury. Look at this histogram at the bottom. At control levels, there's a certain ATP. It's the cellular energy currency in cells. We call them ATP, the energy it produces, which is decreased 60% after a stroke. But if you block all the Ampa receptors globally, you can restore the ability of these mitochondria to produce ATP. This is an example of an experiment which works well in our lab, on our bench, but we can't take it to clinical applications because this is a global Ampa receptor blocker. We can't give it to patients. It will interfere with the normal activity of our brains. So at this point in time, we ask the question of what other ways, if there are any, that we can preserve the mitochondria this well in terms of function and structure. I was a very young assistant professor. I was very junior. And when you see in your inbox, all of a sudden that you're invited to give a talk to Burke Institute, I can't tell you the joy you feel. And I was so lucky and came to give a talk in 2006 about my work here. I was so fascinated with the infrastructure and how comprehensive this institute was taking care of stroke patients and also doing research to improve their life on a daily basis. This is when I got to know about Dr. Fletcher McDowell and learned that his main goal has always been the translation of science into treatment. Being very flattered to be here, I also had the opportunity for the first time to interact with Dr. Rajiv Ratan and his team. And he was working on a field that I have never heard of by then, and he had this amazing results that when he applied epigenetics on his injury mechanisms, there was a profound improvement in the regeneration of axons. I was mesmerized with this opportunity, and I had no idea what epigenetics was. So this was, again, another time that my career took a very different trajectory and opened me a new venue to go about my investigation. First of all, I had to learn what epigenetics is. It's very simple, actually. It's your behavior and the environment that you live in, which then affects the way your genes work. So it doesn't change your DNA or your nucleic acid sequence or anything, but it chooses which part of it has to be translated into function. It's a very powerful system because it's endogenous. You're born with it. You all have it. It's also reversible and has the capacity to change as your needs change. It is very rapid. It can happen in minutes, and it can start protecting you in minutes, and it's transgenerational. It is amazing that if you change your lifestyle and your environment to protect yourself against an injury like stroke, you can actually transfer to this your offspring. So how does it work? You know that our DNA is a double helix. It's a very long structure. You have to pack it in a very nice way into your cell and into their nuclei. It's not easy, but there are these specialized proteins called histones, and the DNA, it wraps around them in a very regular way. It's actually like a yarn. Think of it as a yarn. So it doesn't get tangled. But when you need an information to be translated from your DNA, you can open a certain area of it and you can pick and choose which ones to translate. And the one choice you make, then through several mechanisms within the cell, you form an information which you carry it outside the nucleus into the cytoplasm, and these come as in small information letters, if you will, called microRNAs. And these microRNAs will go find their target messenger RNAs, and together they're going to decide to produce this protein while degrading the other one. And we realized that we can actually use this system in white matter to produce the good microRNAs to support the proteins that are beneficial for our body. And through our studies, we identified several microRNAs that support the production of a protein called MIRO2. MIRO2 is like the hip of a mitochondria, which connects its legs, kinesin and dynein to it. Mitochondria are very motile organelles. They have to run back and forth. They have to be at the right place at the right time to provide that ATP and also help disintegrate the unwanted byproducts. So we realized that MIRO2 levels are very important to keep the mitochondria motile, intact, and functional. So the next question is, are there any drugs that we can activate this epigenetic system with in white matter? The answer is yes. There are several of them, actually, and we have used MS-275 in this case. And if you look at the control, again, these are the baseline levels of mitochondria, fluorescent mitochondria, how they are damaged after a stroke. But if you give MS-275, either before the injury, so you're preventing actually from stroke from happening, or you can give it after the injury. So it's a treatment modality after the stroke, if you will. You can preserve the mitochondria. Not only that, but you can also preserve their function. Look at the level of loss of ATP, which are what the mitochondria produces. But if you look at this columns with SAHA and MS-275, you can actually restore the ability of mitochondria to produce enough energy. And we have compared it with the MBQX, because MBQX is the AMPA blocker, the golden standard for us. So these drugs are as effective as blocking whole excitotoxic injury in white matter. The next question we had is, well, aging is a main risk factor. Does these drugs work in aging brain? And to answer this question, first of all, we had to look what happens to mitochondria with aging. I will need your help again to play my videos. You can play both of them, please. Remember your young axon, the yellow one, which has very smooth contours and extends very nicely. And remember the mitochondria around it, a certain size, dimension, and it covers the volume of this axon. See on the right bottom how thick an aging axon becomes, and the mitochondria gets very long and thick and less in number, so more areas of these axons are not covered by a mitochondria. We confirm these actually findings in our transgenic animals as well. You can see that small little mitochondria in young, how it becomes very thick and long with aging. What is the consequence of this morphological change in mitochondria? It's actually quite important. You can see that the young mitochondria can produce a lot of ATP, but mitochondria from a 1-year-old animal, which will be a middle-aged person like myself, there's only 50% of this ATP being produced. Mitochondria from a 2-year-old animal will be actually producing 1/4 of the amount of ATP from a young animal. Indeed, the decrease in the ability of aging mitochondria to produce enough ATP is one of the reasons why aging brain becomes more vulnerable to ischemia. So the question is, under these conditions, can we still protect mitochondria and white matter function? Luckily, the answer is yes. It looks like if we use an epigenetic approach, you see these thick and long mitochondria producing minimized level of ATP. After an OGD, they disappear and they actually clump together because they're so bulky. But if we use SAHA to change them epigenetically, it protects this mitochondria as good as MBQX, where we inhibit the whole injury mechanism. So at this level, we are working on, we have recently, actually just this week, got the information that all these injury cascades and pathways that we have characterized in mouse also happens in humans as well. We were able to get blood and cerebrospinal fluid samples from control and stroke patients so that we were able to verify the pathways and the molecules that we have identified in mouse does exist in humans and stroke patients as well, and change in the direction that we have anticipated. This gave us the question, can epigenetic drugs, which are already approved for cancer patients, be repurposed for use of stroke patients? We're still working on it, but we always keep the well-being of our patients in our hearts. We do a lot of work to prevent population under risk, particularly the aging population. We do a lot of advocacy to educate the population to the signs and symptoms of stroke. And if our patients suffer from a stroke, we offer them rehabilitation resources, just like in the Burke Institute here. However, we still lack appropriate and functional treatment for these patients, and research develops only the new therapies for stroke patients. So this is why we are gathered here together, that you share what you have learned today, so that you help us educate the rest of the population and your neighbors, your friends, so that you can help us help stroke victims. Thank you very much for your attention, and I'm ready to take your questions.
Questions?
Can I start with a question?
Yes.
So, deacetylation and acetylation of MIRO1 has been shown to alter mitochondrial transport. So I'm curious, in your SAHA experiments where you are impacting HDAC6, perhaps you're impacting acetylation of MIRO1 or MIRO2. Have you looked at what the targets might be that are actually affecting, the mitochondrial movement, the mitochondrial localization and transport that you're seeing? And particularly, have you looked at post-translational modification of MIRO through aging and see if it's altered?
So there are lots of questions,
lots of questions
in there.
It's hard to unpack.
Okay. We know that the class 1 HDACs are important for us, and we know that the methylation is particularly important, and looks like we have more binding opportunities with the HDAC2. However, with how the HDAC2, so we have identified a microRNA called 501, which is a neuronal microRNA. And I was kind of surprised because I'm working in white matter, and why would I have a neuronal origin microRNA? But yeah, axons are, extensions of neuronal cell bodies. We have found that 501, which we don't know yet how it's being regulated by the HDACs, But 501 is actually targets MIRO2. And it's not the only target of MIRO2. ROC1, DRP1, and MIGA2 are the other targets of microRNA 501. And it is indeed, our experiments show that if we regulate the levels of 501, we're able to regulate MIRO2 levels and the motility of mitochondria. But coming back to your question, whether it's through acetylation or methylation, and how MIRO2 is regulating, how 501 is regulating MIRO2, we don't have all the connections yet.
Thank you.
Are there other questions? There's a mic back here too, so.
Yeah. Thanks, Selva. Terrific talk and very clear. So what do you think, is it your hypothesis that there are changes in acetylation during aging that are actually responsible for the aging phenotype, and that what you're doing by adding an HDAC inhibitor is reversing those changes in acetylation, or do you think it's something more indirect? Because you could imagine that if the mitochondria aren't functioning, they're not generating the acetyl-CoA that goes into the nucleus required to acetylate proteins. So it may be a way of improving that balance.
I don't have the experimental evidence for the questions you have, but this is what we're looking at. However, every time we do experiments with aging animals, we almost always get the answers that we didn't expect. And funny enough, for instance, we know that microRNA levels are regulated with aging. We know that the MIRO2, OPA1, and DRP1 levels are almost half, but regulating epigenetically still is working on it. And to an extent that the aging mitochondria almost become young. So their drop in motility, drop in MIRO2 levels or OPA1 becomes irrelevant. However, we did not actually find a change in their acetylation and methylation levels. So it's acting somewhere else, but we don't have that answer yet. There was one suggestion that also from someone else that we should look at the acetyl-CoA levels, whether that's what it's regulating.
So there's a few hundred molecules that are acetylated, and mitochondrial acetylation changes quite a lot with a lot of conditions.
Yeah.
So have you looked at the other few hundred protein acetylations?
No, we haven't. But we are actually doing now more omic approaches, and we're trying to also correlate it with the human data that we have recently obtained. So that we want to go this time from the human data back towards the mouse data to look at it, because, as you've said, there's too many things to look at and decipher which one is important from the mouse data. So we're trying to take a back approach from human to mouse. Yes, of course. Thank you.
Well, I'm always so excited to hear the talk from our last speaker, because, boy, is that not a masterclass in how to communicate? Wow, thank you very much. She's so precise, so clear, so understandable. I mean, that's just awesome. So thank you very much. So we began the symposium today with a presentation on a clinical application to stroke. And it is appropriate that we end the symposium with a clinical application as well. This reminds us that ultimately, all of what we'd like to do is directed toward people. All the basic and clinical research that is undertaken in the effort to manage and treat stroke must ultimately be evaluated in large clinical trials, which are complicated, expensive, and time-consuming. Our next speaker, Dr. Hooman Kamel, has expertise in and is a leader of numerous multi-center clinical trials, and thus his insights will be particularly impactful for this symposium. Dr. Kamel is the Vice Chair for Research and Chief of Neurocritical Care in the Department of Neurology at Weill Cornell Medicine. He is also the Director of the Clinical and Translational Neuroscience Unit in the File Family Brain and Mind Research Institute and the Department of Neurology. Dr. Hooman is, Dr. Kamel, excuse me, is extremely well-published physician scientist who has made numerous contributions to the understanding of stroke and stroke care. Specifically, his research focuses on the relationship between cardiac disease and stroke, and among other things has made the important insight that arterial cardiopathy is a previously unrecognized risk factor for stroke. This and other work has been recognized by the Michael S. Passin Stroke Leadership Prize from the American Academy of Neurology, the Robert G. Seekert New Investigator Award in Stroke, and the Joseph A. Vita Award from the American Heart Association. Would you please join me in welcoming Dr. Kamel for his presentation entitled Tailored Preventive Therapy After Cryptogenic Stroke. Dr. Kamel.
Thank you. All right, thanks so much. It's really an honor to be here at this outstanding institution for neurology and rehabilitation and to be part of this great panel of speakers today. So I'm going to be talking to you about a topic that I spend most of my time working on, which is trying to discover hidden sources of stroke that we currently don't appreciate in clinical practice and trying to come up with better ways of preventing stroke from these causes. So clinically, I work as a neurocritical care doctor in our neuro ICU at Cornell. Here's a picture of one of our rooms, and we can do a lot these days. We have a lot of therapy, some of the things that Dr. Fink talked about, and there are many patients that I think we help sort of prevent brain injury and get them on their way to recovery. But unfortunately, there's many patients that we can't help with our treatment. So we spend most of our time doing research on how to better prevent brain injury in the first place. And a lot of our research focuses on preventing stroke. Other speakers today have mentioned that stroke is the second leading cause of death worldwide. Actually, you can see the burden varies across the world, but in some parts of the world, like China, for example, it's the leading cause of death, and it's certainly the leading cause of disability. So it's a really important global problem, as we all appreciate. And others have also talked about how stroke is basically a problem from lack of blood flow to the brain. And what our research focuses on is trying to understand why patients develop this lack of blood flow, right, at a sort of clinical level. And even in today's era, with all the fancy MRIs and cardiac tests that we can do, about 20% of strokes lack a known cause. So there's some kind of blood clot that has come from somewhere in the body, traveled to the brain, and blocked blood flow to the brain. And in 20% of the cases, we can't figure out where that blood clot came from. And here's a typical MRI of a patient where you can tell there's a blood clot that came, blocked blood flow to several different parts of the brain. And we call these strokes, these sort of mystery strokes, cryptogenic strokes, and that's from Old Latin or Greek, I believe, actually, meaning hidden origin, right? So these are strokes that have a hidden origin, and we can't identify the source. And the biggest problem with not being able to identify the source is that it prevents us from making sure that we're giving the best, tailored treatment to that patient to prevent them from having a second stroke. And most initial strokes are actually pretty mild. And so when you see someone present with their first stroke, most of the time, they, I think, have a very good odds of recovery. But when they have a second stroke or a third stroke, those tend to be more severe and much more disabling. So actually, that first stroke is a great opportunity to try to intervene, figuring out why this patient had a stroke, put in place the therapies to prevent a recurrence. And so it's frustrating when you can't figure out that puzzle. And in those patients, in that 20% of patients where we can't figure out the stroke, there's a very high rate of recurrence. It's about 5% per year. And so, every year, 1 in 20 of these patients who have these
cryptogenic strokes, these strokes of unknown cause, 5% of them, 1 in 20, will have another stroke. And over time, that really adds up to a lot of disability. Go back here. So our group really is trying to focus on where these clots are coming from. And I think most of the speakers today, were neurologists and neuroscientists. They work on the brain itself, trying to figure out, how do we treat a stroke when it happens? How do we help the brain recover from a stroke, prevent disability? And our group, even though we are technically neurologists, most of us spend our time sort of dealing with other parts of the body, trying to figure out, how things can go wrong in the heart or in the liver or other parts of the body, and then result in stroke. And we're really trying to solve this puzzle, where these clots are coming from. And potentially the places that the clots can come from are really, there's two broad categories, right? One, you can have problems in your blood vessels that carry blood from the heart to the brain, so the vascular system. And over time, we know that these arteries can get narrowed. You have cholesterol plaques that build up, and the narrowing can reduce the amount of blood that goes to the brain, or more catastrophically, these areas where there's cholesterol plaques can suddenly rupture, and then a blood clot forms, and that can travel up to the brain and cause a pretty severe stroke. So that's one potential cause. And the other very common cause is heart disease. So over time, patients can develop sort of a weakening of the heart's pumping function that reduces the amount of blood flow that goes to the brain. And then even worse, blood clots can form in that sort of damaged heart and travel up the brain. And these tend to cause the most severe types of stroke. So we call these cardioembolic stroke. And embolism is something that travels up and blocks blood flow. So our group, there's a few of us in the Department of Neurology at Cornell, in the Department of Radiology. We've been working together, and we're sort of working on discovering these previously underappreciated or unappreciated sources of blood clots that can travel to the brain and cause stroke. And I'll walk you through some of the work that we're doing. So my work is related to a condition called atrial fibrillation, which I think Dr. Fink brought up. AFib, as we call it, is a very, very common condition. It's the most common disorder of the heart's rhythm. So patients with atrial fibrillation develop an irregular heart rhythm, and that causes abnormal pumping in one of the heart's chambers. So the heart has 4 chambers, 2 big ones called the ventricles and 2 small ones called the atria. And so the left atrium is one of those 4 chambers. And when it doesn't pump normally, blood clots can form there and then break free and travel up to the brain and cause very severe types of strokes. And so we've known for decades that atrial fibrillation is a big problem. And the good news is that we know, based on decades of clinical trials in humans, that blood thinners can really dramatically reduce the risk of stroke in patients who have atrial fibrillation, right? So it counteracts this effect. The heart is not pumping well, blood clots can form, but the blood thinners prevent those clots from forming. And so it's really crucial to diagnose atrial fibrillation and start blood thinners in patients who have AFib. And some of our work relates to that, relates to better ways of diagnosing atrial fibrillation when it exists. But more sort of at the sort of root of what I spend most of my time doing is working on this idea of that atrial fibrillation is really just the tip of the iceberg. And more, the work from our lab, so to speak, and from other groups is indicating that in many times, atrial fibrillation is just the sort of a late sign of underlying problems in the left atrium that can actually cause stroke even before patients develop atrial fibrillation. And we call this atrial cardiopathy, and it's basically a collection of abnormalities in that chamber of the heart. Over time, that chamber can get thickened, it can get dilated, the cells that line that chamber don't function properly, and so there's more of a tendency for blood clots to form. And we've shown now over the past decades in a lot of different groups of patients where we've used imaging of the heart or looking at patients' EKGs or using blood tests to look at heart function, we're showing that this condition, atrial cardiopathy, is associated with stroke even in patients who don't have atrial fibrillation. And that's really kind of been a paradigm shift of how we think about the risk of blood clots coming from the heart. Because historically, we've really worried about atrial fibrillation, and unfortunately, that seems to just be the tip of the iceberg. And here's an example of some of the early work that we've done on this topic. And more recently, I'm helping to lead a large clinical trial called the Arcadia trial. We're doing this at about 150 centers across the US and in Canada, and we are enrolling patients who've had a stroke, a cryptogenic stroke. So the patients who come in, the 20% of patients whose stroke is unexplained, and then we enroll them in our study. We test them for the presence of this condition of atrial cardiopathy using a few different ways of trying to get at that. And then the patients who have this condition, we then randomly assign them to either take aspirin, which is the standard treatment that we use for patients who've had a stroke, or a drug called apixaban, which is a stronger blood thinner that we use for patients with atrial fibrillation. And so, these clinical trials can be very, very complicated. We've been working on this for about a decade now to get funding for it, to get it set up, to get going. There's a lot of, obviously, you're essentially experimenting on people by giving them these two different drugs. So there's a lot of complexity and safety things to consider. But we're making good progress. We're about 80% of the way done in terms of recruiting patients who have agreed to be in the trial. We have, I think, another year to go before we recruit the last patient, and then there'll be another year and a half of follow-up. So we're hoping to have answers about this condition and the best way to treat it by around the middle of this decade. Sort of on a very similar line, a colleague of mine, Alex Merkler, who's a neurologist in our department, is working on a different chamber of the heart. So I mentioned the heart has two atria, and then there's two ventricles, which are the chambers below. And he is also kind of working along the same line where there's a few conditions that we've known for a long time that if something goes wrong in your left ventricle, that can cause stroke. But more and more, Alex's research is showing these hidden areas of injury to the left ventricle that can also cause stroke. So historically, based on the tests that we did, for example, like the heart ultrasound, you might not necessarily be able to see those areas of injury, but Alex has been using more cutting-edge techniques, using cardiac MRI, and finding that even very small areas of injury to your left ventricle that you might not be able to see using like a standard echocardiogram, those patients have a higher risk of stroke. And presumably it's because, again, you're damaging that lining of the heart and blood clots are forming there and traveling to the brain. And this is a much larger group of patients than we've historically appreciated. So similar to what I'm doing in the left atrium, Alex is looking at the left ventricle. And based on some of these studies that he's done showing this link, right, between damage to the left ventricle and stroke, and also some really interesting data that he got from a different clinical trial where it strongly suggested that these patients may benefit from blood thinners. Alex has proposed to the National Institutes of Health a large clinical trial similar to Arcadia, but with a different patient population. And hopefully in the next year or two, he'll be able to secure funding for that trial. I'm working with one of our radiologists, Ajay Gupta, to look not at the heart, but to look at the blood vessels. So I mentioned how blood vessels over time, cholesterol plaques can form and cause narrowing and lack of blood flow. And the way that historically we have assessed that risk is by looking at the degree of narrowing, right? So we've said if you have a really narrowed vessel, that can basically prevent adequate blood flow to the brain and cause stroke, and that certainly is the case. But more and more, because of advances in medical imaging, we're able to actually see plaques that aren't narrowing the vessel. So we weren't able to see them on our older ways of looking at the artery. And we're discovering these kind of hidden areas of cholesterol plaques in the vessels that go from the heart to the brain. And we're finding that these little pockets of plaque that we historically have not been able to see are really actually quite dangerous and are very strongly associated with stroke. And here's an example of basically on MRI that you're able to see this kind of bright spot that suggests there's plaque there that in our historical imaging tests we weren't able to see. And here's sort of like a figure where we're showing that on the left side of the figure is what, using the traditional tests, what your doctors would say the cause of your stroke was, right? And the purple one, ESIS, is just a fancy term for those cryptogenic strokes. It means we don't know where the stroke came from. It's embolic stroke of undetermined source. And what we're showing is that if you use this more cutting-edge imaging tool to look and be able to detect those cholesterol plaques, all of a sudden you can explain about a fifth of those previously unexplained strokes. And actually, there's a bunch of other strokes that people thought were coming from the heart that in retrospect may actually be due to these cholesterol plaques. So it really changes the way that we diagnose and potentially treat these patients. And lastly, I have another colleague, Bob Aknavi, in our department who is interested in stroke. He did his residency at Cornell, and we have some Cornell residents, former residents here. They rotate at Sloan Kettering, and so they really get an appreciation of the link between cancer and neurological disease. So Bobby's been interested in cancer from his residency days and has done a lot of really, I think, groundbreaking work showing that cancer is a really powerful risk factor for, we've always known that patients with cancer have a higher risk of blood clots in their veins, right? So in the veins of your legs or in your lungs. But Bobby's done a lot of really pioneering work showing that cancer patients are also at risk for having blood clots in their arteries, so causing heart attacks or strokes. And then more recently, he's had some work showing that even patients who have a cancer that hasn't been diagnosed yet, that kind of occult cancer may cause stroke, and then the cancer only gets discovered later. Here's an example of this work. You can see in this graph, at the bottom, it's showing you the time before the cancer diagnosis, so the time is negative, right? So it's 120 days before you're diagnosed with cancer, 90 days before. You can see here that there's actually an increase in your risk of stroke even before you're diagnosed with cancer, suggesting that sometimes there are patients with undiagnosed cancer who present with stroke as unfortunately their first manifestation of cancer. And so similarly, Bobby, to try to figure out how to treat these patients, is proposing a trial to NIH. And actually, he submitted this a couple years ago and has gotten very favorable reviews. So we're hoping that this will come to fruition, called the TEACH-2 trial, where he's going to take patients who have cancer and stroke that we believe is related to the cancer and test different kinds of blood thinners to try to prevent some of that blood clotting activation that happens in the setting of cancer and try to prevent stroke. So these are all examples of work that we're doing at Cornell to try to understand the hidden causes of stroke and then to come up with clinical trials to test different therapies to try to prevent patients from having recurrent strokes. And we're going to do these trials and hopefully find some better treatments. And at the same time, we're continuing to travel further down that road and keep looking for new risk factors to try to chip away at these patients with unexplained stroke. Because to us, in our mind, in this day and age, it really there shouldn't be any patients whose cause of stroke is not determined, right? We should be able to figure out for every patient who comes in why they had that blood clot and put in place the best therapies for preventing that from happening again. And so we're not going to rest until we really try to dig as much as we can into those hidden causes. And ultimately, what we're hoping to do is by continue to come up with new risk factors, discover new risk factors, and do these trials, is to come up with better and better therapies so that we can reduce this risk of stroke. So even though someone might present with an initial stroke, hopefully with time and therapy, like from here, patients will recover, and then we've put in place measures that prevent them from ever having another stroke, and they can sort of live a good life free of disability going forward. And I will stop there. Thanks so much. Happy to take any questions.
We definitely have some questions here. Fantastic.
Thank you.
Well, that was incredible. I'm terrified now. I mean, literally terrified. But my question is, given the 20% and the fact that in all, I think all of the clinical trials that you're either running now or trying to propose, you're testing aspirin as at least one of the drugs. How does that square with the recent advice that people should, not everyone should be taking a baby aspirin? Because now I feel like I'm going home and I'll stop on the way home and buy some.
No, that's a great question. That's a great question. So it's a really tricky topic. So it's true that the latest advice is not to, generally speaking, that people who've never had a stroke or heart attack shouldn't take an aspirin for prevention. And the reason for that is that, aspirin has like a fixed risk of bleeding, right? That is probably the same in most people. So really, you're gonna take that risk by taking aspirin. And so the question is, what is your risk of having a clotting event, a stroke or an MI? And so if your risk of a stroke is very, very high, then the benefit that you get from aspirin is more than the risk of bleeding. So it's a good risk benefit. But for most people who've never had a stroke or heart attack, the risk of getting one is generally pretty low. And so the benefit that you get from that aspirin is actually about the same or maybe even less than the risk of bleeding. So for your typical person, the risk benefit isn't worth it, and you're either gonna get no benefit or actually slightly higher risk of bleeding, including serious bleeding like in the brain, compared to the benefit that you get. But once someone presents with stroke, then their risk of another stroke is very high, and we know that aspirin gives you a very big benefit, and that benefit is more than the risk of bleeding. So. Yeah. Well, they all come out of the blue, but yeah. Yeah, I don't think so, because I think it doesn't, the risk of stroke for someone who's walking around, has never had a stroke before, is very, very low. So I think we're really focusing on people who've already come in with a stroke, and they're just that's a very different risk profile. So I think the general guidance is still to not take an aspirin if you've never had a stroke or heart attack. But yeah. Got one.
Yeah. Hey, Hooman, great work as always. So in my field of neuro-oncology versus stroke, the ability of me to tell patients why they get a certain brain tumor is essentially not possible in more than 99% of cases, right? Which is very different than stroke, because my patients ask, well, why did I get this type of brain tumor? So I'm curious in the field of stroke, about identifying these mechanisms from a patient-centered perspective, other than the obvious thing of telling the patient, oh, you have a stroke because of this underlying cardiopathy, and them feeling satisfaction of knowing the cause. What other insights have you gained from patients in doing this research in kind of ways that they become more engaged with this research by better understanding the mechanisms of stroke?
Yeah, no, it's a good question. It's a tricky thing because in some ways, this whole system of classifying the cause of stroke and then admitting the times when we don't have a direct mechanism, it's pretty distressing for patients. So a lot of patients, you tell them like, hey, you've had a stroke and we don't know what the cause is. It's pretty distressing. I think the reason we still use the system is that you're not going to be able to drive forward and figure out how to discover those sources and come up with better treatments if you're not upfront about it, because the alternative would be to say, hey, you've had a stroke, we have all these treatments, there's aspirin, there's cholesterol lowering medicines, blood pressure lowering medicines, we'll give you all these treatments, don't worry about it, you're getting the best care you can. But I think then that prevents the ability to, enroll people in studies and in trials and try to figure out, what those other causes are. So it's a tricky thing, I think, in terms of the patient impact of telling folks like, hey, we don't know why you had a stroke, but I think it's necessary. I'm not sure if I totally got out your question, but
yeah, I was kind of asking like if they're more empowered to take medications for their stroke if they know them that the treatment that they're getting is tailored towards the mechanism.
Oh, that's a good question. I don't know. I don't know of any data about that. I would presume so, but I think it certainly helps. People want to know the rationale, So like if I'm giving someone a blood thinner for atrial fibrillation, I'm going to explain, what's going on, the heart's not pumping well, blood clots can form. I think that helps that conversation.
It might be interesting to look at those patient perspectives in these trial patients to see
Yeah.
like pre and post, whether their their adherence to a regimen or satisfaction with the regimen is improved because they then know the mechanism.
Right. No, that's a good point.
Yeah, great
Yeah.
question. And just like Terry, I think I'm a bit terrified too because it's rather unsettling. I was just curious with some of your etiologies where it seems to be it's a subtle sort of injury, for instance, in the left ventricular wall. Is it possible then to develop peripheral blood biomarkers for something like this? And does that exist? And is that something that you're also looking at? If it's something that doesn't just rely then on imaging, but perhaps even a molecular diagnostic?
Yeah, that's a good point. I think certainly, so for example, for the Arcadia trial that we're doing, we are using a plasma biomarker as one of our criteria, this peptide called brain natriuretic peptide, BNP. And for the ventricular system, you can look at troponin. That's something that's released into the bloodstream when there's cardiac injury. It's just not, they're not super specific. And so I think ultimately for clinical use, we prefer imaging. But I think that is sort of a gap, right, between the simplistic way that we think about it in terms of clinical research versus what I think could be a much more sophisticated way of doing it if we did some of I like that term reverse translation, right, of saying, hey, here's this phenotype that we think we've identified in clinical practice with our imaging. Can we try to dig deeper into it and come up with a much more sophisticated biomarker panel? And there are folks, where like I was talking to Dr. Lee this morning about looking at protein expression, mRNA expression, who've tried to get at this, and it's a work in progress, and I think it has a lot of promise, and that would be the ultimate goal of being very sure that the precise cause and the precise pathophysiology. But I don't think we're quite there yet for in clinical trials, unfortunately.
Yeah, first of all, congratulations on the many trials that you're really starting, and I think you're kind of pushing the field forward by digging into this ESIS group and looking for subgroups that can benefit from selective treatments. And it looks like where you're migrating towards is personalized medicine, because you're looking at subgroups and so on and so forth. So I really like the idea of exactly what you said, looking for broad biomarkers that can cluster these individuals into subgroups that might benefit from individualized therapies, and that's exactly where you're headed. So
yeah, absolutely. No, that was definitely the goal, and I think that we're trying to do that, but it's still kind of crudely. But for example, for Arcadia, we are collecting blood from all these patients, and it's being stored up at Columbia. And certainly, if anyone has ideas for how we can use that to sort of come up with more refined ways of identifying people and what their response to treatment is going to be, I think there's a lot more we can do. It's very crude right now, the way we're kind of personalizing our care. I think there's a lot more we can do. But thank you. All right, thanks everyone.
Let's get a picture here.
Oh yeah.
Fine.
Well, thank you very much. I'm reminded by the last talk and the first talk and some in between of how important it is our affiliation with Weill Cornell, and so that's been a long-standing affiliation, and we're very proud of it, and we really like our colleagues downtown. So thank you. So this brings us to the end. Are there any general questions that anybody has about anything today that wasn't answered or something else? How was the food? It was pretty good that I had, I definitely would like to thank our staff, our food staff, catering, and so forth. I also want to thank the the IT people here. I mean, we had a bit of a glitch, but they jumped on it and fixed it quickly, so thank you very much for all that. And I personally would like to thank all the speakers and awardees. It was a fantastic, informative day, and I learned so much, and I hope you did as well here. I'd like to ask Raj back up onto the stage here to close this up, but thank you very much for your attendance today.
So I think we would all agree, Glenn, you delivered as promised, and fantastic job. And you know, even though we realize next year we'll have you bring your guitar in case the lights go down. First I want to thank this afternoon's speakers. Takuya is probably sleeping, but Selva and Hooman, fantastic. I think you kept our attention till the very end, and it's so encouraging to realize that we have this problem of millions of Americans disabled from stroke, and that it really is going to require efforts in prevention, efforts in acute treatment, and efforts in repair. And we can't forget that. And I think it's really important for all of these groups to be meeting and talking and sharing ideas, because the brain doesn't think about itself in terms of different epochs. I think it's harder to define the different times of treatment in a human than it is in other experimental situations. But I hope today highlighted for everyone, and I think it's probably been very useful for our faculty and trainees and staff to sort of hear about some of the clinical problems. An event like this takes hundreds of hours of work. There's, you know, I think it's Murphy's Law on a second basis, not a, you know, day-to-day basis. And I think we would all agree that there's many people, and I'll get to them, but there's one person who really has driven, maybe one in close second, which I'll mention, who's driven this effort and has always, you know, no matter what happens, is enthusiastic, positive, and we'll get through it, and that's Christine. And Christine, please stand up and take a bow, because yeah. And you know, I was wondering, you know, I was thinking, you know, we love the Rosedale room, but you know, there are always challenges in the Rosedale room, but I was wondering, could we just leave the tent up the whole year, keep all of this here, and you know, we've been dealing with the problem of where are we going to put our new auditorium, but I was thinking, wow, this is perfect. So you know, it would be wonderful to be able to meet here as an institute regularly. And I have to say, you know, everything from the background to the video screens, it's just it's really the best event that we've had. And the person who's a close second, and then many people who contributed. So is Liam here? Back there. Yes, of course. But when you go by, find Liam and say thank you, because I think Liam did a lot of work as well. Bree is obviously Christine's right-hand person, but there are lots of volunteers. And look at this list. I don't even know how I got on this list, but but it's an incredible list, and I think it highlights something that's really special about the BNI, and that is whenever we ask anything of anyone within the Institute, they are always willing to step forward. And the one person who I didn't mention this morning, who I wanted to come back and be sure to mention, is Sungi Cho, who runs our you know, our stroke program, and you know, is done amazing research here in developing a chronic stroke model. but also I think has been important in keeping Selva close to us, and we hope that will continue. So I think this is the end of the day. I mean, I'm tempted to say, where's the bar? No, but I think that we didn't plan that. And I think, again, I'd like to give a round of applause for everybody who attended, and we really appreciated having you. Oh, there is one person who I also can't forget to mention, and that's Darlene, because, you know, the dynamic nature of my schedule is really a Rubik's Cube, and she does an amazing job. So thank you, Darlene. All right, have a great afternoon. If we have any therapeutic recommendations regarding anticoagulants or other things, we'll email you. All right, take care.